Hola, ¿cómo están?
¿Qué tal?
Bien, ¿tú?
Bien, bien.
Ok.
¿Qué tal, Leo?
Hola, ¿qué tal? ¿Cómo te va,
Ah,
Alejandro?
bien, bien, gracias.
Bueno, me encanta.
Okay, I think we're live now.
Yes, yes. Really working.
Okay, perfect. Okay. I'm receiving the presentation. Satoru, I also made you co-host, please.
Okay.
But I think I can share the screen for you. Satoru and Michael, Diego, it's also a professor of the course. I think he's the only one Colombian. All the other professors aren't from here.
Hi, Satoru. Hi, Michael. How are you?
Hi, how are you?
Hello.
Doing well.
Good. You? What about yourself? Good.
So maybe let's wait 1 more minute so the students can join us.
Hola, Plinio. ¿Cómo vas?
Hola, buenos días, ¿cómo están?
Hola,
Bien, ¿tú
Plinio.
qué tal?
Hola, Daniela, hola a todos.
¿Qué tal, Plinio? Buen día.
Buenos días, Alejandro.
Okay. I think we can start. It will be recorded anyways, but I don't want to start too late. So I'm gonna share the screen 1 second. Okay, so let's start. So the professors of the course, which are Diego Perez, Carlos Navarro, Alejandro Alcalá, Agustina Lainez, and Plinio Perez, also the School of Architectural Design and the University of Los Andes, and myself, Daniela Tencio, would like to welcome everyone to the series of lectures and tutorials as part of the course Computational Thinking, or Pensamiento Computacional in Spanish. This is a brand new course of the Architectural and Design program, and couldn't be, I think, a better way to end this first version that we call Print Hello World. Listening, interacting, and learning from people, academics, friends, and colleagues that are really pushing the limits of and leading computational design in the world, and that are really an inspiration for us and our students in what we do in the course. So the agenda for today and for tomorrow will be the following. Today we'll have Michael Pryor, then Satoru Sugihara, and then William Virgil. And tomorrow we'll have Gabriel Esquivel, Casey Ram, and Nicolas Turkey. Everything will be streamed on YouTube, and it's live right now. So welcome, everyone. So to start, we have been using for a while, and in some of our classes, I think the coolest Grasshopper plugin, which is called Pufferfish, and it couldn't be a better way to start today with the person who developed it, Michael Pryor. Michael is a multifaceted designer utilizing Rhino, Grasshopper, Maya, ZBrush, Houdini, and others. He's currently a computational designer at Nike NXT and CEO of Design Morphine. He has been involved in various major architectural works in the US, China, Dubai, and Lebanon. Previously, he worked at Trahan, Soma, Oli, and AYA on projects ranging from museums, housing, restaurants, furniture, products, exhibits, and prototypes. Michael is the author of the popular Grasshopper plugin Pufferfish with over 100K downloads. He has been the tutor to workshops by the AA Visiting School Paris with Louis Vuitton, 3D Dreamin, RISI ARC, MIT OSL, Harvard GST, Rad Lab, PA, Meal, and Design Morphing. So welcome, Michael.
Hi, thanks for having me.
Have you here.
Can you hear me?
Perfectly. So
Yeah, cool. Thanks for having me. Yeah, so I'll just share my screen now. Okay, yeah, so I'm Michael Pryor. Thank you for the introduction, and thank you all for having me and inviting me. It's good to see like more of these kind of classes popping up to get people into computational design. I'm a computational designer at Nike's NXT Digital Innovation, design director at Zymorphine, and author of Pufferfish. And I just wanted to take the time to talk a bit about kind of where kind of unexpected places computational design can lead you because it's not directly attached to architecture. So it opens up a lot of different possibilities, and also to talk about like creation of Pufferfish and why I made it. So my kind of background is kind of like, and my work history is kind of like all over the place, like this kind of crazy, map, and a lot of it like unplanned and unexpected. So I went to school at New York Institute of Technology, and from there I kind of split into work and education, and through these different architecture offices and different teachings throughout the world, I kind of was opened up to a lot of different possibilities and organizations and collaborations, which eventually ended up from me kind of going from architecture to more and more computational stuff, and then to away from architecture completely into product design at Nike as a computational designer. So what a large part of my kind of work now revolves around developing tools and workflows and distributing those tools and workflows. And they don't need to be crazy complex. They can be simple things too. So that's another thing kind of talk about is, how to use these tools to even just optimize small parts and redundant parts of your workflow. And, a large part of that started from, a lot of the teaching I was doing, and like what we're doing in Design Morphine is just when you interact with a lot of students in a workshop environment where things are very short amount of times. You're talking like 3 days to maximum 9 days. You start to see like, well, first of all, you want to get the maximum amount of output in that small amount of time because it's not the size of a semester of college. So you start to see what kind of things, like what kind of processes slow things down or people struggle with in those short amount of times. And you want to kind of see how to optimize those processes so that they can kind of get past those, in my opinion, like maybe more unnecessary hurdles to get to the output. And that was a large part of why I created Pufferfish 2, which was like a way for me to optimize a lot of my workflows. And that's why it grew so quickly in the amount of things that it does. Because every time I was doing something and I felt like this could be easier, again, even small things, I would just, make something to make that so that I didn't have to do those things anymore. And I always like this quote from Bill Gates where he talks about he'll choose a lazy person to do a hard job because a lazy person will find an easy way to do it. And it's obviously not necessarily real lazy people. It's just saying that this kind of mindset can help you get things out of the way quicker. And something interesting, like if you look at all of Autodesk's software, they actually have charts of all the commands that are used and what order those commands are used in and what they're used in connection with. So you can start to also make connections on like the types of things people are doing a lot. And funny enough, in all of their software, the most common thing is deleting, erasing, and undoing. So we also make a lot of mistakes all the time, which I think computational thinking also helps you kind of remove that boundary as well, because the kind of system building of computational design is the idea is that you don't have to undo or erase things. You can just change inputs and parameters. So if you look at something like, I like to look at things in a kind of simple sense. If you look at something simple like a grid, if you were just to do this kind of grid on paper, there's a lot of setup and a lot of pre-work that needs to be done just to get a grid. And you already know you want this grid that's like this size in this direction. But if you were to make it, traditionally, you would have to get something to measure with, you would have to get something to draw with, you would have to get something to erase with, all these kind of steps just to create a grid. And then you look at something like software like Rhino, where it's a bit easier, but if you look on the kind of like top left here, it's like you're kind of just like repeating commands over and over again. It's pretty redundant to get the grid. And then you can use even more, condensed commands like array, let's say, but still requires some setup of inputs, and you can even go further and put those kind of things in macros. But still, you have to redo that every time. And then you move into something like Grasshopper, which is like kind of parametric computational thinking, where now you don't have to do all that stuff to like make the grid. You're just giving the instructions for the grid, and those instructions are variable. So you can just change them, and the grid appears there. And so taking that onto the next level, kind of like of tool building, where you're scripting and looping, you're taking those ideas, defining a square, drawing a line in U, offsetting it in V, repeating it in V, and then the same thing in the other direction, and then creating closed cells. If you can take that process, you can run it in a loop, and then you have your tool there, and you don't ever have to think about those steps again, right? It's there, and you can use it. And the nice thing is when you're doing this is that it's also more flexible, so you can use this now. You can not just make a grid, but you can make a grid on a free-form surface, on whatever. So it also makes the tool, I think, these things more usable. And if you take that like to the extreme with something like Finch 3D, where it's the same kind of idea, it's just a lot more input and variables. But if you break it down, it's really something like an extreme version of grids, right? So you're just creating boundaries, and the system is trying to figure out how that works, how that looks, how that lays out, what kind of space that makes, based on rules and standards and parameters. And then even further with the kind of stuff that ZH Code is doing at Zaha, where it's even to the level that a client can interact with it as well. And this is really important because clients, they don't necessarily understand things like building codes and required hallway widths and bathroom sizes, right? So it's kind of like they don't need to think about those things. They just need to know what they want, right? And then the system that you've developed or designed should figure that out for them, right? So you can get people involved in your process that don't even necessarily understand the process behind, because they don't necessarily need to understand that process. And with these kind of things, a lot of like the kind of criticism would be like, well, like, isn't that kind of taking away from the job of the architect or the designer? But I would argue, that we've already been doing that, just in a more manual way, right? We all have books that are about standard references and floor plan references and CAD blocks and this and that, downloads from websites, like manufacturer websites for like sofas or tables or whatever. So we're already and have been looking at these things. So why, if they're standards and factual, why can't they just be embedded into the system so that you don't have to every time, look through this chapter of this book to find this thing? So there's a lot of these things that are, requirements or standards or suggestions. So I just think like it's really an interesting way to get rid of those bottlenecks in the design process. So which is kind of like an automation of design, where the kind of designer is more a system builder and curator than like a manual doer. So the benefits, the automation, like to reduce obviously the redundant repetitive work, just like time to focus on more important tasks. You can reduce human error and in repeated operations. I can't tell you how many times I or have seen people, do things like copies and offsets and things are off by small amounts, so you reduce, you start to reduce those kind of things. You improve productivity, speed, and execution, because you're offloading things that don't necessarily need a subjective aesthetic point of view onto something which is much faster than our brain, a computer. You can remove learning curves and training efforts by distributing tools across a team. Everyone can have the same set of systems and tools, so you can try to not have people at different levels or different understandings of things. You can have everyone on the same page working in the same systems, and you can have an integration and distribution of that workflow, as I said. Which brings to kind of why all of that kind of together is why I created Puffish, which is my public tool, and then there's a lot of like not public tools for offices and my work that have the same kind of principles in mind, which is just always about like a lot of stuff I make in Puffish. Some of it is quite complex, some of it is super simple, but it's always about kind of workflow optimization and just making things easier. And actually, the kind of start of Puffish happened at Trahan Architects. When I joined, they were working on this theater in Atlanta. I think it was bought by or paid by Coca-Cola, so I think it is actually called like Coca-Cola Theater. But anyway, the entire interior was these steam bent wood strips that needed to perform acoustically. So strips needed to be at different, different spacings between them for acoustic absorption panels, or different tightnesses so that sound can bounce off of them in certain ways to hit certain rows. And it was all kind of laid in there and mapped by lasers and then bent and fixed into place there. As you can see in this diagram here, in those mock-ups, how the spacing is changed. And the one on the right, the wood strips don't necessarily follow the exact curvature of the surfaces. So this was how I created the kind of tween the curves on surface, which wasn't a tool in Rhino or Grasshopper yet, but was something we needed for this kind of process. In the end, they were pretty far along with this when I joined, so a lot of it was done already. But it gave me inspiration to kind of create this tool and use it for kind of rest of the process. So when you have a surface, NURB surface is comprised of a UV grid, but that UV grid isn't necessarily always following the design direction that you want to kind of maybe flow things or place things along. So we needed a kind of measurable way to break that grid, but still be on these surfaces so that we can control things like density and pinching and spreading. So that was like the first version I made there, which was like also the input should be easy for that. So it was like you had some guide curves, and then you can blend along those guide curves, but along a doubly curved surface. And you can see a mock-up there on the left. And so, to do this process manually was kind of annoying and cumbersome, which is what you had to draw. First, you had to have the 3D surface, and then you had to draw reference curves on the surface, and then you would have to unwrap that surface and the curves with it, then do the blending, because then you can blend without the kind of the 3D surface interfering with the directionality of those things. And then you would have to map all that back to the 3D surface, which is, kind of simple enough for someone experienced with Rhino for one panel. But if you imagine an entire theater's work that needs exact and certain kinds of continuity, it could be pretty painful and redundant process. So the idea was just to like package that up so there were, all that was happening behind the scene in code, and you just input the parameters needed, and then there was a few different types of ways to do this as well. So that's why there's the 3 components. You could do it between 2 curves, or consecutive between curves, or through like a bunch of curves. Now, things like Grasshopper and other node-based editors are really good at kind of finding these kind of use cases and packaging them into components or nodes, which we have a lot already. But sometimes, sometimes the software misses kind of organic use cases, which is something I was also after. Apart from building tools that were of my personal interest or workflow, I was looking a lot on forums to see like what kind of things people are trying to do often or are struggling with or always asking over and over again how to do it, to kind of get a sense of like a new person that just comes into us, like what are they trying to do that's not available to them. And you can, if you look at something like an attractor, right, like it's like kind of something that's, I think, really simple. Anyone that's familiar or with computational design knows what an attractor is. It's kind of like computational design or parametric design 101. But if someone's just jumping into it, they don't know. And if you actually search attractor like on the forums, you'll see there you'll have over 500 results, and that's just on the new forums. That's not even taking into account the 8 years of the like past Grasshopper forum. So in my case, and there's a few other like plugins that have done their own take on these things. So in my case, I was like, okay, so like, what's my take on that? And first I made there just a simple grasshopper definition that would set up the kind of system I wanted, and then I scripted it, and now I don't have to think about it anymore. Like, I have the tool there, I just have the inputs, and I think that things like this and this kind of mindset is a big player in why pufferfish got so popular. Is that there's just stuff there, it's like ready to use, but it's also flexible. And as you can see here, I spend entirely too much time on the forums, a lot of time. So, but that just let me see a lot engage in what kind of things people were trying to do, and then also all the kind of education stuff as well, like I mentioned in the beginning of the presentation. And the way I go about this, and then I think anyone that is looking or interested in computational design, or if you're taking this class, at some point you'll be making tools as well, just because it just always ends up there. I don't think I've met anyone that, even if it's not distributed, you're always kind of making little systems and processes. For me, the best way is to, and I was doing this in Grasshopper, is to, anytime you have an idea, or if you're working on a project, like this process is taking too long, it could be easier. Like, I just write it down. And so, like, for me, writing it down meant like just making an empty Grasshopper component that said the name of the thing, potential inputs, outputs, and a description. And then I would just get to making the thing whenever I had the moment. But just to know that, like, there's this process that is could be simpler, or something you just don't want to do anymore. You just get it there, document it, and then you can make it when you have time, or when you are a little bit more knowledgeable on how to make it. And so that's what you're seeing here. This is like what one of the kind of development files of pufferfish looks like. It's just kind of like a mess at this point, but the stuff is there. And you don't even need to make such complex things to make an impact on the community or the people around you, or even yourself. There's a bunch of components in Grasshopper that aren't difficult, but in my opinion useful, like things like x-1 or x+1. You would think like, well, why would you have that? But these are kind of things that are so common in like scripting and coding. For instance, in loops when you're counting, or simple things like percentage. There's no percentage component in Grasshopper, and it's actually kind of I just noticed that, like, a lot of people don't actually know how to calculate percent. Like tipping math, like if you're tipping at a restaurant, this kind of stuff. A lot of people end up just Googling it. It's just one of those things that's really easy, but a lot of people just don't remember exactly how to do it. So simple things like that can actually make a big difference in someone's workflow. And I didn't realize it until I in one version of pufferfish, I was like, oh, maybe I can just like obsolete all these kind of simpler components. And like the next day, I was, as you can see there on the left, I was getting kind of emails saying like, why did you get rid of those? I use them so much. So I didn't realize how many people were using like even the very simple components, and it was just important to their workflow. And I equate it to things like where Mark Zuckerberg was saying that he just wears the same clothes every day because it's just one less thing to think about. And that's kind of like what these little components are. It's just like one less thing to think about. Just get those out of the way. And then, so the other thing is like when you're making these kind of tools, there's kind of a balance between doing too much with the tool and not doing enough. You don't want a tool that locks someone into a specific outcome. You want things to be flexible. so that's why have there like to do all the things, and it's like no, and then it's kind of broken up into the kind of steps. You want to modularize a bit so that the system is flexible. And that's why in this case, for instance, like to do this, there's 3 different components. There's the first component, which creates what Grasshopper calls twisted boxes on different geometry. And then you have another component which lets you, for instance, like blend meshes. So you can create different kinds of panels. And then another component that lets you put these panels into those boxes. And the reason that, you know, in my opinion, you wouldn't want one that says like, okay, here's an input geometry, and then it's gonna, you just put the panel and it just panelizes it, because you want to have different control over like the kind of transformation space. You want to have different control over what is a panel, and then you want to have another control of actually performing that operation of panelizing. So there's just kind of like a line there that of kind of modularity. And then, of course, there's other Grasshopper components involved in this case, depending on what you're trying to do. But the overall point is flexibility in the system. And that's why, like, if you look at things like Ladybug, you know, that component's entire use is in kind of environmental analysis. But it's broken down, in my opinion, in a very smart and useful way that you can understand what things do, but you can also plug and play and kind of only use the kind of processes and things you need. And the way that they break it down is like there's geometry preparation, and then there's analysis preparation, and then there's simulation, and then there's visualization. All right, so that's kind of like the way that they broke it up. And there's all these kind of things depending on what you need, rather than it just being like one whole thing that's just like, okay, here's put in your geometry and output, you know, everything that has to do with analysis for that. And same with some stuff like BIM and Revit, where, you know, you're not just like getting a building there, everything is put into components, right? There's walls and floors and ceilings and doors and schedules, but all these things kind of come together to make the overall final product, but they can be used and tweaked independently. But you have to be careful, again, like not to lock the user into one outcome. It's really important to give flexibility, as I'll keep reiterating. But in you know, for instance, and this is just a funny example, but you know, in the example of like Voronoi, you know, it's not really the Voronoi diagram's fault. It just happens to look also interesting, but it's not actually made for that. You know, it's for space planning and connectivity diagrams. And because it looks so interesting, it often gets used incorrectly, which is like for its aesthetic properties, which don't necessarily mean anything, like unless there is some kind of structural analysis behind some of them, but often it's just kind of like pasted onto a facade. And actually, if you use Voronoi too much in Grasshopper, you'll get this kind of developer warning from the developer that tells you that you're lacking in artistic vision, basically, which is kind of funny. Because he also knows that people are using it too much for like the aesthetic properties versus the real kind of connectivity and space planning properties. And so that's why we come to this meeting here, which is like he finds and he completes his design thesis. And yeah, so this is another like set of components. It was broken down in 2, which is like this discrete vectors, which just makes like these continuous flows into more angular flows. but again, broken down into the vector directions and then the process of finding the closest vectors. But if for this one purposely, I didn't make any component that actually makes the flow of these things. So I left that up to the user. So the user can draw this flow manually, or they can run it in a loop with some looping plugins, or they can just write a loop, really up to the user. And then basically this two components transform whatever kind of flowy thing that they've made into this kind of discrete angled flow. Another important thing to consider, like when you're making tools, especially if someone else is going to use them, is consistency across your tools. And I like to think of it as kind of a matrix, and the matrix is like if you have the idea for a tool, on the left you have, okay, what are the different ways to execute that idea? And then at top is like, what are the different geometries or the kind of different substrate of that idea. So if you look at something like tween, which is basically Rhino's blending of curves. In my case, I have tween 2, which is like blending between two things. Tweening consecutively, which is blending between a bunch of things, but like as sets. So from A to B, then B to C, C to D. Then tweening through, which is like actually just considering the whole thing at once. And then on the top, you have the geometry type. So for color, curves, surfaces, planes. So you wouldn't want to like someone who have a plane and for some reason they don't have the same kind of flexibility as the curve or a vector. The other important thing is parameter and input naming consistency. For instance, if you call something a factor and it's the same kind of thing somewhere else, you should like it should still be like factor instead of possibly something like amount or amplitude or it's just a consistency in naming, so that also when people see a tool, even if it's for a different type of geometry, it's expected that they understand how to use it. They don't have to learn a different way to use it or what a different thing is every time. Another important aspect of tool making and distribution is the kind of interface. And in this case, again, like Proficient Grasshopper, so the interface is really like icons and descriptions. And the thing like with the top, Pufferfish one is on the bottom. In the top there, you have, and again, these two that I'm talking about up here, the one with the robot arms and the one with like the blue squares, they're actually very good, very advanced plugins. But from a user point of view, they're quite difficult because in the top, every robot is in a different position, but it's not obvious enough, like how, like if I wanted to find a specific component, unless I knew exactly the name, it's not quite obvious, like the differentiation between them. And then the next one down, every icon is the same. So that just like makes, in my opinion, like an unnecessary barrier to the user. And icons don't necessarily even have to, they don't have to exactly look like the thing that they do. They just need to be recognizable so that when someone knows they want to do something, there's something that they can associate with, even if it's over time after using it. It's just like super understandable. There's a relationship that's made once you start using it, that this icon does this thing. The other is the descriptions. You want to be, I think, very thorough in your descriptions when distributing tools to people. The more they know, the less emails you'll get asking you what things are. And for instance, again, like the one here with the blue squares, the descriptions are also like the same, just as the input. So graph, isolated vertices. But if someone's not like super experienced with that plugin, like they're not gonna know what that stuff is. The next thing is like always to kind of test your tools against like unexpected use cases, or even just distribute it to like your a closed group or some friends, just to see where things go wrong and where things fail. And that's what you see here on the left is like a first version of the tween curves, and on the right is the second version, and the second version is like a lot more lines of code, right? Because it's like finding errors, finding different conditions. Like 90% of the process in these kind of tool creations is trying to prevent people from using things incorrectly or to find different cases. And it's, you know, one of my early kind of funny ones for me was this kind of mirror cutting of meshes, which has a lot of I mean, it looks simple when it's done, but you know, even Rhino itself just added a symmetry in its 7th version, because there's just a lot of conditions to think about and the way things hit each other and meet, and how do you you know, blend that together. And my first one, I was like, and it was also when I first started coding, so I was like pretty happy that I resolved that. And then as soon as I put it out there, like a few hours later, someone sent me the screenshot on the right that it wasn't working on an open mesh, and I just had completely like got so into like these two cubes that I didn't even test it on open meshes, and it didn't work at all. So it was like that kind of thing really made me think like, okay, I need to start like testing things more. And then I went back, and you could see, you know, the component went from like these 4 inputs to these like many inputs. A lot of them can work just as default inputs, but it was working for all kinds of meshes and arrays. So I was pretty happy about that. I would say it's pretty stable at this point. And, you know, bringing me to a next level is like the documentation of your tools. So apart from like icons, descriptions, you want to make sure that there's examples, whether it's through videos or files, so that people can follow and understand them. And, you know, Parfish has example file for every single component, and then also workflow examples, and they're all annotated and described and documented. And I think this is also like a big reason why a lot of people use it, is because they have that instruction manual there. It's like less intimidating, I think. When you see a component like this with no description and all those inputs and outputs, it can be, or even bigger, it can be like pretty intimidating. But when you have the instructions that's clearly telling you what's what and how it works, it kind of, that intimidation just goes away, and you realize like it's a lot easier to use than it looks. And here's just some example stuff on the that you can do kind of like out of the box with Pufferfish. And these are on the download page as well. Some of the kind of workflow examples. And it's really funny because there's so many examples that people were making like some memes that I was tagged in Instagram about the example files, which was, I think, really funny. So I thought that was really, really funny. You know, another really important part that in this whole computational thing is like just to realize that none of us are doing anything new. We're just building upon other people's things and combining them in different ways. So it's really important to credit. So just wanted to throw that in there. Just make sure you credit. Also, the community is just too small to not do that. You know, just make sure you credit, you know, the things you use, just as you would an essay or. And you know, for me, an important part is like listening to the user feedback and consistently updating things, and just trying to make things easier. So this is like this is just like all the different versions where things were updated and fixed and added. So what, you know, the most fun part for me is like these are all stuff from not that I didn't make, like that people made, and like I'm constantly tagged in like Instagram and Facebook, or even just emailed like images of things people are doing with it, and there's just like such a big variety of stuff, between like lighting fixtures, or like graphic designs, or like spatial arrangements, or just kind of interesting geometries. The one on the left was they're using mirror cut to make like helmet variations for some character. You know, jewelry. The bottom left was someone's Burning Man. I think they're, because they was doing like a VR Burning Man. Someone's Burning Man proposal. Top left is actually a real wall texture. Some abstract stuff. 3D printed jewelry. A lot of people are using it for. On the top left there, someone actually used it to make their tattoos. So I thought that was really cool. And you have in the bottom right, like someone recreating the 3D printed outsole footwear. And the top left, like someone used it to make like a real stone tiling system. People are using it on footwear, and the bottom right was at I believe at EAC. They were making some pavilion for one of their workshops using it. Yeah, so just like a lot of stuff that's just like all over the place, which I just really found fascinating, like all the different ways people found to use it. And one that I really liked was there's this one guy, he was remaking all these like architecture that we all know and admire, using pufferfish. So he was remaking like all the facades, and he put them online for free. So he was doing like this one from Zaha, and then the other one there, and like the DSR one. So, and like actually like really good detailed versions of it, not like just faked. I mean, that like DSR one looks pretty legit. So I thought that was really cool too, that he was, you know, remaking them with my components. And then at you know, in design morphing with our workshops, like both physical and digital, a lot of the workshops and webinars incorporate pufferfish. So like pufferfish obviously isn't the only thing making all this stuff, but it is a part of it. They're like always using it, just because it like just makes some parts easier. So these are just some, and some are more obvious, like the second from the left down, this one here. Like some are more obvious where it is, or some are less obvious, like what exactly he was using. And again, like more design morphing and workshop stuff. And in the, well, there's some physical stuff here too, but in the more digital as well. Stuff just using pufferfish in different ways. And the other interesting thing is that at some point, other organizations started making tutorials for pufferfish. So that was cool because I didn't have to make them anymore. So that was really helpful. But it was also helpful for me to see how other people that would teach with it would use it. And sometimes I'll see the tutorial and be like, I didn't even know that you can use it that way, even though I made it because I just wasn't thinking to use it that way. Or sometimes I'll see them use it and I'll shoot them a message that like actually you can do things easier if you do it this way. So it's just a lot of like kind of back and forth learning. And then in my teaching, I like to work at like this kind of scale. I find it like a lot easier because you don't have a lot easier, I guess, for teaching the tool because you don't have to worry about architecture, which is just like a lot more complex. You don't have to worry about the technicalities of I don't know, stairs and this and that and facade complexity, and it's just like a lot easier just like learn the tool this way in a short amount of time. But has a lot of the same principles that could be potentially brought over into architecture or something more complex in scale. And I also like to be pretty abstract in like when I'm teaching it, because again, like I don't want to stick to like just a defined kind of outcome. I like to be abstract and then let the students like figure out how to then take those systems and use them in a way that's maybe more practical. And and then I'm always like playing with this kind of stuff, and it's not even just Parfish. Like again, it's sometimes Maya or ZBrush or Houdini. Just always trying to like test the limits and see what kind of like weird things can come out of it. Because when you go kind of like really crazy or too far, you can then like take parts of those learnings and kind of bring them back down to reality. So you learn a lot by like pushing things further than what might actually be achievable. Although a lot is achievable now with 3D printing, but it's just a really good way to like not to be concerned with reality and technicalities. So I suggest always to kind of do these kind of explorations that don't always need to make sense or end up as some resolved object. So yeah, I mean, I'm sure like if you follow me or are familiar with the work, I'm sure you've seen a lot of this kind of digital nonsense, but to me it's my helpful way of getting things out, and kind of more just like brainstorming and sketching. It's like a digital sketching for me. And it's just really fun to like learn a lot of just different processes, because all these things just take different inputs, different processes, different combinations. So like the first real thing that I used Pufferfish for was for these crowns for wedding, and they go like I guess they're called wedding crowns. They just kind of go on your head during a wedding, and so my wife and I wore these at our wedding. So that was really cool. Like that we just made them. They actually like broke on the travel, but luckily we were able to glue them together. They didn't break too bad. And then more recently was this lamp that we did in collaboration with Arturo Tedeschi, which was a really cool process because it involved a lot of different manual and digital things. So it was like a handmade Murano glass, and then so we had to kind of like estimate the shape, have them hand make it, and then we had to scan it because it's handmade, so there's imperfections, and then we had to bring that scan into Rhino, and then we had to design the kind of the 3D printed part within that scan, so that it would fit and so that 3D printing part is designed mostly with pufferfish components and tools, and then we had to hollow the thing out and channel it properly for different lighting. So we did like some lighting analysis, some digitally like lighting analysis to see like kind of how the light was diffusing through the object, because it's when you're kind of creating channels through these things, they're thicker in some places, thinner in some places, and we wanted the light to kind of like, if you can see it here, we wanted the light to kind of like go away more towards the edge, and be brighter more towards the center. So just looking at a lot of those things computationally and analysis wise. And also there was, because it was like made in Grasshopper and Powerfish, you can see there's kind of two different versions in the bottom left. And there was actually like a lot. There was probably like 100 something of those. And they were just super easy to like iterate and make and see different versions. And eventually we landed on this more like ovally shaped because of the limitations of the kind of handcrafted glass shapes. Something that we could at least predict a bit in the outcome. And that brings me to, bringing this to computational design and product design brings me to Nike, which I can't talk too much about, like exactly what I'm doing at Nike, but this is one shoe that just came out. That was one of the first ones I started working on, which is for Kyrie Irving. It's a Kyrie 7, and I worked a lot on this. I worked a lot on this product. And this product actually was the one that helped me learn a lot of stuff. And it's mostly like through like performance, performance product. And the reason why I just wanted to kind of transition that way into these products is, like, if you look at something like Food for Endo's website, if you look at the categories and the charts they have, there's so many categories revolved around this thing, and this is just Grasshopper. Like, if you go imagine all the other kind of parametric, computational, generative, whatever tools, like there's just so much more available and community-wise than architecture. I mean, architecture here is the largest, but there is a lot more other possibilities. And that's just looking at that. It's just if you think about it at the core, it's just like a change of scale, right? It's just in the beginning of the process, and then afterwards, the process changes based on construction and manufacturability, or like what you're actually doing with the thing. But just in this example, if you look at like a footwear, tattoo, and automotive architecture, you can see that in this case that pattern is pretty similar everywhere, and it can go on and on: jewelry, furniture, sculpture, movies, games. And if you can look at things like, for instance, this Parakeet plugin made by a friend of mine. Everything, let's say in that case, can start from this kind of 2D pattern idea, and then it's what you do with it from there, which based on what like you're actually trying to make. So if it would, and those are the limitations you should consider too. So if it was like something like a tattoo, you'd want to be considering like the thickness of a needle, or how detailed can a human actually draw, versus something like that's made by robot arms, or things with sheet metal for a car. Or if it's for footwear, it's like what kind of things can be injected, molded, and demolded. For a facade, you're looking at, depending on what it's made of, if it's stone or metal, you know, just again, there's different types of limitations and methods of make. Or if it's something like digital, like a video game or a movie, then you're really looking at things like polygon counts, you know, those kind of processor optimizations. And you know, in at some points that kind of can be consistent, and that's why, you know, my transition from like architecture into like product design, sneaker design was pretty seamless. Like, you know, like going from Trahan Architects to Nike was like such a huge scale change, but I never felt like, oh, I have to, like, I don't like it's overwhelming, I have to do too much, because actually the, you know, like the tools and the workflows for the most part were the same. You know, just the difference was the kind of manufacturing. So again, like I kind of try to base this around like Parfish and the tool creation, because if you're interested in comp design, more than likely you're going to be making something at some point that someone will be using. And it's just, these are kind of like the successful tool kind of recap for me, which is like to make sure you document your workflow, you break it down into modular processes, you list each tool's like process, you have consistency in the use expectations, you have it be easily identifiable to the user, anticipate use cases and conditions, have clear and thoughtful documentation, test it thoroughly with other users, credit anyone who helped along the way, and then just to kind of release it. And I like this to end here, like with this meme here, you know, for people trying to learn this kind of stuff. It's not as scary as you think. It just takes time like anything else. So that's why there's this, you know, how do you get started? He's just putting him in front of the computer, you know, so yeah. So, and then, you know, we're kind of moving those, you know, all those processes we're also incorporating into our workshops and master's degrees with design morphine. And yeah, if you want to keep in touch, if you don't follow already or have any further questions after this and after our, I guess we'll have a Q&A or after a discussion, feel free to reach out. I don't really pay attention to LinkedIn or Facebook, but if you really want to reach out to me, Instagram's the way to go. I'll usually answer pretty quickly. So yeah, and that's all I have.
Okay. Thank you so much, Michael. It was incredible and really inspiring. We're relating a little bit with our classes too. And I'm sure they will reach out, everyone. So we'll still maybe 10 minutes from Satoru, but I think it would be important maybe to have a few questions. I don't know if maybe some of the students would like to ask something, so feel free to jump in. Who will break the ice?
Is there a place I can see the question? Or would it be in chat?
No, I think they will just ask the question.
Yeah.
Or the professors too, or anyone that it's here.
Yeah, maybe I start asking a question, Michael. I was wondering, how has your work as a designer changed since you developed pufferfish? I mean, how has that changed the way you address a design commission or design task?
Yeah. So yes, I mean, since I developed, I mean, it's kind of back and forth, like, because pufferfish has also changed because of the design task too. So like anytime I work on some design, I try to like take those pieces and see if I can bring them into Pufferfish if they're useful and not like specific enough, like that they can be useful for other things. And then using them in my workflow, I mean, it's definitely like just made things really a lot faster because I just, after so long using something, like I've been using Grasshopper for, I don't know, since 2009 or 10, like, so like pretty long time. You just get tired, like you just realize, and I'm sure any of you, if you're using Grasshopper every day, all the time, you just get tired of doing the same things over and over. And you do end up doing like the same things over and over. Like how many times have you remap some numbers for an attractor or this or that? So it's like, it's definitely made a lot of that stuff faster. But I would say it also has definitely like influenced my design style as well, because of the kind of system that it is. But it is based on my, a lot of it is based on my specific way I like working. So I'm not sure if it changed it so much, but it definitely made things faster and easier. Because I can't always remember everything also. It's like when you write a code or a definition and you go back to it months later and you're like, what did I even do here? So.
Yeah, I kind of noticed
Having a hard time hearing.
better?
No.
Carlos, there's a lot of background noise when you open the microphone.
How about that? Can you hear me, guys?
It's better, yeah.
Okay, I'll just ask it like this. Yeah, I mean, I like what you said about when you were developing this tool, how you tried to not to lock the user to one outcome, right? And try to leave it open-ended, like an open-ended tool set. So I would ask, how has the community development through the years influenced your actual development of the tool? I mean, pufferfish is becoming more known these days, and there are pretty interesting outcomes that are similar, in the community. I mean, do you find yourself developing more tools towards I don't know, a certain aesthetic that is becoming more on trend, let's say?
Yeah, I think there's a lot of ways to use it, but I think some ways are more obvious than others. And it also comes down again to like the Voronoi slide there. It's like, I think a big reason, and it's not like to kind of put anyone down for that, but a big reason is that I think there's example files and people open those example files and those example files do specific things and have a specific outcome because they're just example files. And I think like the example files, like they look really cool on their output very quickly, or really interesting. And so I think people maybe often kind of play it safe and stay within that example file, and kind of just like tweak things a bit so things look a bit similar to the things that I personally put online or do. But there are cases when people are getting more comfortable with the tools. Like it depends on like the person's involvement in the tools too, or how much they're willing to experiment. Because I've seen things made with Parfish that honestly I don't even know how to make it. Like, you know, so I don't know how they, like, what they did, or, you know, so I think it's just like a few different levels or type of user, and kind of the level of involvement they're willing to engage with the tool. And it's not just Farfish. I would say that goes for anything, you know, even just, you know, out of the box Grasshopper. And that's where you get the kind of Voronoi facade user versus, like, you know, the whatever, you know, other kind of interesting things. So I think it's just two different user bases. But I think people who are less experienced, they open Parfish and they get like super excited because it's like the first time that they can get this kind of geometry on their computer, and they're just so excited about it. They kind of like tweak it a bit, render it out, and it looks cool, and which is cool also. You know, I like seeing that stuff. Like, and I hope that like that kind of empowerment like influences them to go further. I mean, kind of that's like kind of the hope. But I would say that there's no single component or node that would like get you those things. They would all rely on the input, and that's again why like the workflow examples have inputs already in them, whereas the components, like something like this image here, which obviously has a mirror cut across it, right? You know, if I put a completely different geometry in, it's not going to look anything like that, right? So if they just use the mirror cut component, it would heavily depend on like what's the thing they're mirroring and blending, versus if they open this example file, which already has that geometry input, you know. But I would say there, like, I don't know how to define it, but there is definitely like a kind of style, you know, emerging that I'm not even sure it's just Farfish. Like, it's kind of like a lot of, there is something emerging there, but it is hard to define, like, kind of computational style. It's there, we all know it's there, but it's hard to say exactly what it is, I think.
Okay.
I mean, I found it really, really interesting and useful for discrete aggregations. And I don't know, maybe it's generating a style.
Yeah.
So I don't know. It's just really interesting. Thank you.
Thank you.
Okay. So, well, I don't know if a student would like to ask the last question, so we jump to Satoru's lecture. They will have an extra point.
Yeah.
Well, so I think I'm pretty sure they will reach out to you in private.
Yeah, they're shy, maybe.
So thank you so much, Michael. It was really, really great. And it was really an honor to have you today with us.
Thank you for inviting me.
So much for waking up at 4 a.m.
Anytime.
Okay. Well, feel free to stay if you want to stay. I know you're busy,
Yeah.
but we'll continue here.
Sure. So I guess I should stop sharing there.
Okay. Okay. So now I would like to introduce Satoru Sugihara. Satoru was our professor, and I think he really influenced our career in a way. And it's a real honor to have him here today, actually, with our students. So welcome, Satoru. Satoru is a principal at the Computational Design Studio, ATLB. Prior to start his studio, he worked as a computational designer at Morphosis Architects in 2007 to 2012. He publishes computational design software IGEO and taught seminars at SCIARC in 2011 to 2017, and many workshops in LA, Paris, Tokyo, Vancouver, Bilbao, Taipei, and Hangzhou. He received his Master in Science in Computer Science from Tokyo Institute of Technology, and in 2001, the MArch from UCLA in 2006. So welcome, Satoru.
Right.
I'm going.
Sure. Thank you very much for the introduction and this opportunity. So first, let me share my screen. Yes. Okay. Do you see the screen?
It's sharing. Yeah, now we can see it.
Okay, good. So yeah, I think I'm gonna mostly talk about the architecture project, but anyway, first, so again, my name is Satoru Sugihara, and so I'm a computational designer, which and then practicing as my kind of own firm, which is actually usually work as a consultant for other architects, and then I mostly design facade for them. Then, so as Daniel mentioned, I have computer science background, and then most of my work is coming out of processing, and then you might see difference, but that's not the point in this lecture. And then so because Michael gave us really good kind of a framework, a kind of conceptual framework of computation design and tool aspect, and I just give you super quick history, but not necessarily about tooling framework, but more about like how people start use algorithm and numbers to design something. So in my view, one of the kind of origin is John Maeda, who used to teach at the MIT, reading in Media Lab, reading kind of a computation group focusing on aesthetics, and then but he was a very early person to start writing text code to produce, in his case, graphic design. So then that's not just like automate the graphic design. It also came with the expression of number and expression of algorithm, and then most of the time expression, or actually most of the algorithm is based on repetition. So meaning then of course he attacked an area like where the type of work which human hand cannot produce, meaning drawing something million times something. So it comes with a specific aesthetics which is tied with this kind of idea of repetition, and so that also led the work to more about kind of complexity in a way. And as a successor, out of his, John Maeda's laboratory in MIT, Kay Sirias and Ben Fry came out with other students, and they are working on the software platform called processing. Actually, that's what I usually use for my practice. But anyway, so they pushed this approach to actually they made it popular for designers. Like they produce the processing is kind of a text coding platform for beginners, basically. Actually, specifically for designers. So and then, but now that kind of it became wider target, and then that including like music to video to instruction to media and many things, and including architecture. So that's why I use architecture with my own library on top of it. But anyway, so that's kind of a context I usually work on, and then that's where I came from in a way. And then, but I gonna show you architecture project, and then. So as I mentioned, when I work as a computation designer, I most of the time design facade and complex facade, and then that involves this algorithmic way of thinking, but also the reality of construction as well. But that is strongly tied with the geometric knowledge, which make the construction possible. But anyway, so I show, but I'm gonna show a bunch of morphosis projects and then other project as well. But anyway, first one is a Fair Tower project in morphosis, and by morphosis, and that's originally that was a competition in 2006, and then so I worked on this project as a computer designer, and they would design the facade and also designed on the glazing fenestration and then structure. But the project was the skyscraper in Paris, and then the height is the same with the Eiffel Tower, which is actually the maximum height allowed to be. And then it's located in the area of La Défense, which is a business district. Unfortunately, this project was cancelled after Lehman shock. Well, actually, it survived the Lehman shock for many more years, but at the end it didn't make it. But anyway, so I designed the facade, which is actually out. That is actually secondary facade outside of glazing panels, and then that's a solar shading panel made out of stainless steel mesh. And then, so as I mentioned, I applied computational technique to 3 areas in this project, mainly facade skin, and then secondary glazing, third main structure, the diagrid structure. So about facade, so as I mentioned, I mostly work in processing, but the way of working or parameter way of thinking are all the same in Grasshopper or any other, or Revit or other platform is the same. And so I start with, first in this project, there's a designer who designed the form, together with Tom Main. And then I take that form and I extract the surface of the building. And then I build grid inside it. And then I put some geometry. So in this case, I create an internal orthogonal grid on the surface, and then I put diagonal panels. Then I put a pattern on it. In this case, it's slightly rotating. So that kind of process is actually kind of layering structure. So you have the grid building part, and you have the geometry allocation part, and you have the patterning part. So once you set up, you have tons of parameter inside it, and you can change that. You can swap the logic, or you can insert the logic. In this case, the grid spacing is all different. And in this case, geometry allocation is different, not just diagonal, but in diagonal panel on both directions. And you can insert some random algorithm into it, and you can control a randomness by some other input, or you can specifically apply the logic to continue certain panel on the diagonal line, or etc., or gradient randomness, etc. So that kind of process of building up algorithm, putting algorithm on top of algorithm. So you just keep adding layer, or extract, exchange, adjust, etc. So that is the actual iteration of design, especially in my case. Then, so that was, this geometric technique I'm talking about, like a very specific geometry generation technique, which I'm calling striation, which is based on the internal grid of the building, and then running geometry along it, or either kind of vertically running it on the surface, or horizontally or diagonally, and then differentiate them. So adding controlling the panel length randomly, or offsetting randomly, or removing randomly. So with some pattern layer. In another case, in this case, panels are slightly tilted randomly to give certain dynamic sense, and then plus it was separated in different layer for different materials, etc. In this case, the panel size is kind of all the same. This is supposed to be kind of plastic membrane panel for Middle Eastern project. This is all photo by Morphosis, and this was competition entry for Kapsak project in Riyadh, which we didn't win. But anyway, so in this case, the primary purpose was to give solar shading. That it's harsh sunlight in Saudi Arabia, or that in Riyadh city. So, but we wanted to give a maximum view to outside. So the horizontal is very open and then very close to the solar direction, and then but still giving certain kind of cloudy kind of sensibility to, as with movement of around the building shape. And another project in this case, the architect is Studio Linkark, and then so this is a kind of a gallery building in China, and but it started with a kind of bunch of studies of like a panel side. Okay, so building grid. So grid size definition and the panel shape definition. So parallelogram panel versus rectangular panel and or triangular panel. And then grid could be randomized. I mean, like some panel is double high, some panel is half, etc. So that kind of logic can be applied or inserted inside and still play with the diagonal panel, etc. So, but just keep generating tons of options, then to see if there is any construction issue, I mean, a cost issue, or of course the architect. So where I work, the consultant, I work with architects, so they make this design decision, and so of course for them to tie the whole geometric style to design ethos all together. So I generate a bunch of options together with the geometric knowledge and construction knowledge. And at the end, in this case, a kind of simpler one, but also still tied with whole building sensibility. And of course, cost is figured out as well. And similar type of project, this is elementary school in Shenzhen by Studio Clark. And then start with a bunch of options. In the beginning, I generate tons of different styles of design. And then, but then when the project goes on, we kind of limit the option, then they tame down, and then in this case, actually toward the end, the grid is really become orthogonal grid and panel rectangular. Although there's a several different, we came up with several different modules for the kind of different profile and the kind of channeling profile, and then especially checking like a corner condition or building is I mean, straight in the curvature, and we didn't want to actually for cost purpose, or we didn't in this case we didn't want to unnecessarily complicate the project, so we didn't want to put three-dimensional panel around the corner. So we wanted to have the flat curvature panel, or we didn't also want to segment it. So in that case, we limit the kind of extruded channeling panel only in the flat area, but we need to test make sure that can work as a whole building. So plus this is also kind of cost analysis, and this is but this is a kind of imitization verification, like which panel can be exact same size or same panel, actually in this case same type of panel. And then but curvature is most of the time kind of special, but all other parts can be unitized the same unit to make the construction efficient. Then, but anyway, so that's a constructed building. Then another type of algorithm or kind of geometric technique, which I call field effect, where you have tons of similar element and similar kind of component of geometric or panel, in this case panel, similar panel, but you tweak that little by little, and then to cover whole surface, and then as a result you get this kind of continuous blurry effect. And in this example, it's controlling two angle of panel. And I applied that technique to the Morphosis Emerson College Los Angeles project, and in the courtyard facade. So this building is actually, so this is satellite campus university building. Actually, this is easier to see. And then this is actually a combination of school building, classroom, and the office, and dormitory. So this is actually the both side. This box shaped part is a 10-story tall dormitory building. So both side, and the west side inside, and then this is satellite campus of Emerson College. Emerson College is based in Boston, which is East Coast, and then but their TV and the movie department is very strong, and so this building is for students to come to Hollywood and to do internship in Hollywood studio during summer, and also take class. So this is kind of summer internship program satellite campus. So students live here in this 10-story tall building, and then occasionally they also take the class in the classroom, which is located in the middle of the building. So then the facade I built is actually a separation of the private dormitory space and the public classroom space. But actually, there's a courtyard which for students, I mean, for lunch break or after they come back from the internship work, they hang out there, or occasionally or weekend they do film screening, etc. So that's a separation. This facade is separation private space, the public space. But I wanted to make it really appropriate for art school and then really dynamic and then creative atmosphere. So I designed this folded aluminum panels, and then this kind of like a flow like or ripple like condition is created there, almost looking like responding to the other part of the building. But the computational process is basically so I have the idea and I built this folded panel. So actually I also developed kind of a simplified origami algorithm inside my library, and then so that can generate a folded panel. I mean, some sheet folded shape, but that is controlled by this grayscale shape in the first phase. And then so this grayscale image, actually I generated that in the Photoshop and just not really painted, but blurred technology. And then that controls the shape and also the spacing between them. So that controls the density of the pattern and the shape, or like orientation or the grain of them at the same time. So once I set up that script or like whole workflow, then now I can switch the middle part. And so in this case, I start with a rectangular folded panel, and then I could still switch to triangular panel, and I also could layer the panel in the front and back, and using different bitmap or grayscale image, or putting some randomness or different type of image to control that. So that's the type of study I just go through quickly. And then of course to discuss with some main, which is the direction we want to go, etc. But this approach of like a field effect, like just tweaking something a little by little to have the certain kind of bigger pattern, you can apply to the vertical ruler, and you can apply to horizontal ruler. Actually, this is study for the outside facade of the Emerson College building. So like to register some clarity pattern with the horizontal ruler, and then the bottom is in case we cannot purchase the individual ruler control system. If we need to control like by unit, then that bottom one would be the appearance. But anyway, so even if you have like a fixed panel size, you can register the pattern by like just controlling the spacing between them. Or if you have to close everything, you can control, or you can register the pattern by controlling the panel size or panel height, then express the whole pattern by the seam and the density of seam of those panels. And actually that was designed for the atrium in the middle building. But anyway, so that's so second type of technique. And then, but from here, I start talking about more kind of construction related efficiency or kind of geometric mathematical issue. So for this project, Emerson College, there is 1,500 panel on one side. So for both sides, there's a 3,000 panel. And then I try to make it as smooth as possible. However, the smoothest option gonna be costing the most. So because each panel gonna be different. But I mean, this is typical thing to do in this kind of a work, but I unitize them. I mean, even though this looks smooth, it's unitized to 15 different panels. And then, but half of them is a flipped shape. So actually the 8 different panel unfolded, and then that 8 unfolded shape is actually stuck or fit together perfectly together inside the sheet metal, aluminum sheet of 4x8 industrial standard. And then, so actually, so to reach this point, we went through really many iteration. But the thing was that first, yeah, we wanted to minimize the waste. That's one thing. Then, of course, but we didn't want to maintain the continuity to the maximum level or acceptable level. And then another thing is that this knowledge came only after we chose fabricator, but when we find fabricator and they talk to them, they decided to use the water jet machine to cut these panels. And then for that, the cost is determined by the use of minutes of that machine. That's a primary factor for the cost. So to make the panel cheapest, what we need to do is we have to cut the panel fastest. That's the cheapest panel. So to cut panel, and when you need to cut 2 panel, and if you cut 1 line to produce 2 panel, the price is half. So we try to overlock the panel as much as possible. That's how this kind of interlocking L shape is coming. So, but anyway, so that's so that kind of knowledge comes suddenly in some day. And so as a competition, I just respond super quickly, and then we just move on. So, but anyway, but that's a final kind of pattern or design. Then also we need to also consider some other stuff, like it was originally supposed to build the whole facade is pre-assembled in factory and shipped to the site. To do that, you have to have the pre-assembled unit to fit at least on street. So there's the truck bed size. So we have to divide those units and not to harm the whole pattern. So that kind of study goes on. Then this is a different project, but using very similar approach. And then this is also for morphosis project, but in this case, the unfolded shape, like a folded, unfolded approach. In this case, there's 6 different unfolded shape, but I folded each panel 6 different ways. So as a total, there's a 36 different 3-dimensional shape of panels. Then this project was an interior design project. So this is a restaurant bar project. And then I wanted to cover the ceiling and the wall with those panels. So that was a kind of my approach. But problem is that each area is not rectangular and not even trapezoid because this is twisted shape. So problem is that I have 36 panels designed, but I don't know which panels go where. And plus, I have option like a slightly rotating or slightly shift offsetting, etc. So I wasn't sure, or it wasn't clear that which panel should fit the best where. For the solution, to solve this issue, the approach is just simply check them all. So 36 panel, and then maybe with 1 millimeter increment of shifting, then 0.1 degree of rotation, there's a less than 1,000 different options for each. And for computer, checking 1,000 is totally no problem. Actually, I made this animation just to present, but in reality, this computation is done within second or less than second. So, but anyway, so I just made a full search. I just ran full search algorithm to find the best panel fitting. I mean, best panel fitting without colliding to each other. So, well, actually, basically what happened is the project area maximization. So, but anyway, so in that way, so I allocated which panel goes where, and on top of that, there's a graphic designer work on all the texture. Actually, there's a graphic film applied on top of the folded aluminum panel, and then this is like a sports themes slash fashion themes sports bar slash restaurant. So yeah, that's how it came out. And next project, and then in this project, actually this is also more for this project, and then in this case the facade was flat, and I needed to put the solar shading panel outside the glass panel, and then but in this case I was specifically interested in creating some condition of a kind of ground figure condition, like a figure or like a opening also look like figure, but the panel is also a figure, so kind of blur the kind of opening and the closed part to each other to unite hold the face of the building kind of aesthetically. So but anyway, so this situation went through, and also this project has some limited budget as well, so I limit myself to use less than 10 different modules to do that. And so, but anyway, I went through a bunch of options and studies, and then at the end, I have 10 different panels, modules to cover whole building. And then this was for the Morphosis project of Bill Gates Hall at Cornell University. And then, so you can see those kind of transition from like a flat panel to open, more like a fish scale like or dragon skin like panels. And but that kind of dynamic sense was something I was aiming for. And then, but anyway, so this is one photo of showing the panels, and then also the reflection panel. So the glass panel is a super very reflective glass panel. So you also see the front of the facade panel, and you also see the glass, and you see the back side of the panel, and you see the sky of the other reflection, etc. But anyway, so there's a tons of visual or optical layer there as well. But anyway, so that's design process of this Cornell Bill Gates Hall facade. And another type, this is also kind of modular approach. This is a finance city tower in Morocco. It completed last year. And then in this case, also, yes, we wanted to keep simple for facade. So we kept everything modular in a certain level. And then, but yeah, first thing is that we needed a solar chain, actually Ruba. We wanted a Ruba in Morocco, but we also want to really double down the kind of aesthetics in this kind of crystalline like building shape or a sense of not really rock, but anyway crystal. So we kind of went towards more like a solid sensibility, and but still functional Ruba, and with this kind of crystalline geometry or kind of diagonal cut, etc. Or diamond cut. And then so we went with this diagonal Ruba. I mean, almost vertical, but kind of diagonal Ruba with some solid accents. And then so that was kind of completed photo of that. And then so yeah, we made it like a really kind of solid stone like Ruba system. And another project, this is a residential house in Singapore by our architects. And then in this case, after they designed the house, they asked me to, they wanted to cover the whole house with perforated metal. They knew they wanted to register a certain tree pattern, but they didn't really kind of the full kind of exploration or iteration process, or what tool to use, how to generate the whole digital fabrication information to produce. Actually, this is not really digital fabrication. This is actually a traditional perforated metal makers fabrication. So we need to generate a drawing for that. But anyway, so I took care of that part, and then they wanted to use this special perforation, which is like this tab. You don't really punch out the hole. You keep the part of the circular material, then push it out to have some tab, or it's something called tab perforation. But so then actually that they are also thinking about using this as a louver or for solar shading as well, which is quite clever. And then, but anyway, I started with like a tree pattern. So they were also interested kind of not really nature tree, but could be computer generated tree. So we kind of went through the whole iteration of what kind of tree to project. But at the same time, we start talking with actual perforation metal fabricator. And then because this is a traditional, it's not laser cut or water jet. This is like a punched metal fabrication, which is used punching machine and die. So set of die. So they produce limited number of die to press the metal sheet. So we have limited option of like circular shape, circular size, or even location. So at the end, the tree pattern became super simple, and then just a bunch of branches. But on top of it, of course, you have to think about like where is the private area, where is the public area you want to make it open, and where is the location you want to have the more shading, etc. So that kind of information is all kind of figured as the bitmap or grayscale image. And then at the end, this is like a computation process diagram. I have all the geometry information and the tree branch information and the perforation size information and the folding. So to take advantage of the tabs as a ruler, I have to control the orientation of that as well. So I have the information as well. And there is like a privacy area, like a no fault, some area. But anyway, I put the whole thing into processing. And then this, I mean, this is actually kind of longer code, but anyway, that's that generate whole 3D shape, I mean, geometry in Rhino, and also like line drawing. Actually, first it just generate the whole building line drawing as a 2D, and then second, everything, each chunk is converted into DWG file. So at the end, I got this 180 sheet of drawing, I mean, automatically, and then this was sent to the fabricator, and then they can produce the panels. So that's how it works. One more project, actually, several more projects, but more projects. This one is Istanbul City Museum, and this one is still under construction. And but anyway, so this is, the architect is Salon Architects in Turkey, and then they so I work with them, and then first I explored all the kind of modernized Middle Eastern arabesque pattern. But that was the first round. But the second, we kind of picked certain pattern, and then one kind of circular arabesque pattern, and then another more hexagonal one. But each of them has an option like this transform shape. First, yeah, that was for the grain definition of the facade pattern to match with the building shape. But that's the more important, this is also thinking about the construction grid, how efficiently we can pick up those panels in where. So that kind of iteration or study goes through. And but at the end, actually toward the end, too much more with the building shape, we went with the parallelogram shape, and about all the like perforation studies and the pattern studies, and then but at the end it's kind of calm up, although really subtle, and so but that's a kind of final option, and it's under construction now. Actually, this photo is like 1 or 2 years ago, so it should be much more done now. And another project, Milan Expo China Pavilion, so by Studio Linkwork. So that's Milan Expo, that was 2015. And then I designed the roof facade, actually roof, but it looks like facade. So so this is a diagonal panel roof facade. Is actually woven bamboo panel on top of metal frame. I mean, this is this is built in Milan, Italy, but it's a Chinese pavilion, so they use the Chinese bamboo to build the roof. And then, but this form of the building came from the idea of like a Chinese landscape and also Chinese urban scale, so quite complex shape. But so the translating complex shape to the buildable shape is some the whole other aspect of work I did, which I gonna talk after some other project. That's a back of the building which represent the cityscape of China. This is the interior design project plus facade. This is also by Studio Linkwork and Ken AUD. This is a restaurant interior design, and then that's actually kind of recent one or last year. This roof, not roof, this is ceiling panel is a kind of organic shape and leafy shape. Somehow client was interested in kind of organic design somehow. But to realize that, I started with kind of simple grid, and then trapezoidal, and then randomize flip by flipping, and then creating double unit, etc. But also need to differentiate the density. So that then each different density represented by different module. And then, but that was made out of same kind of sub module, so it's kind of efficient. Then, so that's the seating, and it's actually made out of painted perforated aluminum sheet and then welded together. So That's then same in the same way the facade was designed. Although facade is a bit more complex because extruded same profile but the cut in 3D or elevation, so a bit combinatory complexity there. But anyway, so that's completed roof or ceiling panels. Then kind of technique wise, so those are the stuff I was showing. The first, all the facade is kind of geometric technique, and then but this is more like algorithmic, different type of approach, and then use of dynamics, and which these days you can easily do with Kangaroo. And for example, the diagrid building in that complex shape is sometimes cannot be done in traditional way, and then in that case you have to do that with this kind of thing to make it smooth. The Emerson College also at the end, like a final phase, I used force simulation to control the pattern. And you can easily do the minimal surface stuff, which I used for some competition for lobby design. And then form form findings are very common thing to do with this technique. And then design like just use or just define like a connection point or the tensions, strength, and etc. To then run the script to generate a form. But that's not that new thing to do. It's not that different from what Gaudi did. We are just doing digitally. So still do. Then other aspect is the relation. So this is more really about construction. And then when you have the maximal smoothness, most of the time that's the most expensive option. So you have to maximize the repetition of certain element to make it rational and cost efficient. And so that process happened in this case of Federal, and then there's some legal issue, not legal, but some many factor why it happened in this way. But the one thing is that when you decide to repeat where, that part is not necessarily automatic process. You just use your geometric knowledge, mathematical knowledge to do that. But what's automated is the gray area between. So this stitching is automatically done by the physical simulation I just showed a second ago. So I just can decide where to be same panel, but then my script just automatically stitches them together to make it look all smooth, and it just remove the seams between them. And then for glazing division, and then in the beginning, this Fair Tower project has just a projected diagrid pattern to have the flat panels, but that had a problem like generating two tiny sharp triangle, which is not so. If the glass panel is too sharp or too narrow, you cannot produce because it's gonna be broken. So in that case, you have to fill those area with the metal panel which look ugly. So but anyway, so we had that problem, and then we went through many iterations. And then one time I just noticed I can approximate with a conical shape, and then that's what I did. And then plus, then I have this visualization algorithm as well to generate whole, like to count how many panels same and how many different one there, etc. And this was also good communication too for like contractors as well. So actually, this project went through site like they already we had a general contractor. They start construction, then the project stopped. So we actually work with general contractor until some point. And even in the case of Milan Export, start with geometry. So in the early phase, the geometry wasn't necessarily green because I was working together with architects from the competition phase, and then when competition, you just quickly generate the whole thing and for rendering, and then but later I have to make the geometry buildable or rational at least. But rational, making rational is a first step. It is super simple thing to do, which is just try to maximize the amount of straight line, and then try to maximize flat surface, and then if not conical or cylindrical surface, and if not conical surface. But that's the process. And then, but then to build a facade or some panels on it, first you would build perfect grid and the perfect panel with no gap or zero tolerance. But after from that zero tolerance or unique shape panel, then you unitize them. You approximate like a slightly bent panel to totally flat one, or like a very bent panel to just one single folding, etc. So to then you have certain tolerance for to do that, and you have certain target to achieve. But anyway, so in that way you can make it the whole facade system efficient. And even joint is problem, and then usually the disjoint issue and the facade panel is kind of tied together. If you usually there's a trade-off relationship. If you make the facade panel super efficient, then the joint gonna be unique. I mean, if building is kind of a unique shape, and then if you make the joint super rational, then the panel is not rational. So, but you just need to find the best balance to do that. I skip some technical detail. But one thing you need to remember is the this kind of rationalization. This somehow became a kind of professional competition designer. He used to be a professional structural designer in the past. But anyway, there is no ultimate answer to that. Never. It's all just a balance. If you want to achieve super smooth, continuous, beautiful thing, it costs a lot. And if you want to really simplify them, unitize them, and then segment them, it's not ugly, but it's just defined looking, not smooth thing. What you need to do is you just need to provide, as a designer or as an architect, you need to find the range, and then you need to present it to the stakeholder, I mean client, who can decide how much money they can put to achieve what quality. So as an architect or as a computation designer, I just generate those options and explain how it works. Then some other kind of quick thing up. Another topic of rational quality, optimization of solar performance. In this case, Fair Tower has I put algorithm for each panel to optimize them by themselves by checking the location of solar, location of the sun in front of their panel. So because each panel is oriented different direction, so some panel in the south is optimized for the sun at noon, and then panel on the west side is optimized for the afternoon, and then the east side is optimized for the morning. But this is just a result of one algorithm for panel to find the location of the sun to optimize for. And then, so actually that was all the kind of construction project talk of mine, and the rest is my educational activity and the research. So I think I just go quickly, and then similar to what Michael did, I have my own tool published on public, open source on the web. But this is a library for processing. But this is actually just a result of my work. When I practice, I developed tool for myself, and then later I published that on site. So that's how it works. But I also taught those on the in SciArc and other workshop as well. And some of them more for the swarm simulation, and then some other geometric operation. Yeah, it's a swarm generator 3D prints. This one is just a kind of two-dimensional use of a swarm for some graphical pattern. But anyway, let me skip this part through. Not that important. Some branching algorithm try to generate a structure, and then using that for some competition with KUD and another one. That was some competition of conventional center in China on the site where the already built, so we lost the competition. Other thing like this one is Grasshopper Python. So I was also teaching Grasshopper Python course in SciArc, and this is specifically using a subdivision algorithm. And then I asked students to write to do custom subdivision, and there's those type of work. And then, but also interested in complexity, and then certain specific type of complexity. I think this is Daniel and Alejandro's work, I guess. But anyway, so those are complex geometry. First of all, I ask students to run script right before computer crashes. So you just try to kind of reach a limit. But anyway, so but one specific thing I asked the student to do was that try to find the quality of complexity which doesn't go all over to chaos, but still having certain harmony, not necessarily harmony, more like kind of a homogeneity or some certain type of consistency there in a way, but still super complex. So that was a kind of type of work I was first primarily what I'm interested in, but secondly that's some to me important thing to pursue. And then, but actually same line of interest, what kind of also continues to some studio teaching. So I taught some studio course in China this summer, and then but that was on urban context. But I was kind of same kind of approach or target. I will ask students to pick certain urban context and trace to extract a complexity, actually generate complexity, but still tied with the context, and then try to find the type of, still architecture, but kind of urban formation or architecture building, which has a complexity with okay, kind of differentiated quality and homogeneity or like a consistent quality at the same time. So that was some kind of things I pursued. Then slightly going back to more agent. So another thing other than the kind of complexity aesthetics, I also very interested in the agent approach, which is originally came from nature. So like a agent approach is coming from complex system science in 1970s, and so once I ask students to find some example from nature to explore mechanism of how it's built. In this case, the students generated or wrote code to simulate the mushroom growth, and then model something out of it. Something abstract. And as another student look into bacterial growth to generate certain type of formation geometry, and but that's kind of things you can do easily in processing, well, together with my library. But then specifically still tied with that my kind of interest in the complexity, kind of heterogeneous but still kind of consistent complexity. So in this case, I had generated like a swarm algorithm which keep changing its behavior, and then but still kind of maintain certain integrity. But you see that many define the geometric condition, which is a result of behavior change. Gradient behavior change, and yeah, so that kind of generation is something I like. Then, but once I ask myself, like, what can I do with for architecture? Well, maybe something physical at least. And then once I challenged to build something like it, and then which was, installation I did in Los Angeles. And then, but one thing is I cannot just generate whatever line or whatever trajectory form. It wouldn't stay as a structure. So to stay as a structure, somebody need to make it as a structure, which I've done with a structure agent. So there's a two set of actually several agents. So there's the one is swarm agent, but there's which is currently kind of flying around in this plan view. But there's also the structure agent which is left behind the swarm. So all the kind of vertical line, diagonal and vertical line, and also horizontal line, there's a structure agent. And then the vertical one is tension optimization agent, and the horizontal one is a complexive structure agent. And so they are trying to find the kind of state of equilibrium, and when they can have the stable state, that's the geometry you can build in the state. So that's how this self-optimization works. And then I applied the same logic for some other projects, like to design the pier. This one is just a kind of imaginary project, but I generated this for swarm formation first, and then did the physics or structure simulation or structure optimization second to make it work as a pier structure. So it's suspended pier structure. I mean, of course, it's super expressive and then not necessarily structure efficient, but I mean, the whole kind of it's complex, but still works as structure. And then that's pier in London Thames, having like a park on the river, and then like using the wire is a kind of tension structure, but all the colorful ribbon is a shading device. But anyway, so that's a one design project, and then occasionally I look into other type of algorithm. In this case, a cell growth algorithm, and then I just quickly go through. Well, actually, let me just show you the architecture project at the end. So I just go through a bunch of like algorithm development and then type of mechanism, parameter, switch, control. But what happened was, so I developed like for several maybe months, I was developing my own algorithm. But later, I met some other architects who is doing similar thing at the time. And then we worked on interior design project, which is this. So in this case, I designed this light diffuser selectorized kind of structure fixture in China. And so the overall project is the collaborating architects, and they also have developed their own cell growth algorithm, and we kind of work together to realize that. And so in this case, so those whole strip is what this shape is generated out of this cell growth, and then it grew from the kind of initial simpler shape to this shape with a certain differentiation of the panel shape, etc. That's kind of a reflection of the construction process, and also that kind of expression of that. And then there's of course digital fabrication process, which I believe many of you students are gonna work on at some point, but some structure analysis, and then the whole like how to unfold everything in efficiently, and the packing and the laser cut, and then assemble by hand. Actually, in this case, I mean, I made that production as efficient as possible, but at the end, it's still kind of super complex thing to build together. The building or assembly is still kind of manual process, so it's not that simple. But anyway, so that's one project, and then this is another. So this is all our project part. Their cell growth algorithm generated this shape, and then they build that. So maybe I just talk on maybe the last project, which is a kind of tutorial. So I skip the whole expression of the algorithm, or kind of a premise of the workshop, and to the end. So let me jump to the last slide. So I taught a workshop this summer, the digital as a part of Digital Future World. That's an online digital kind of conference and workshop. So it was supposed to happen in China as a real annual conference, but it didn't happen because of the current situation. So, but anyway, so I taught this workshop, and the student built this. And this is some specific algorithm I've been developing several years, which is about kind of modularity. So, and then so it has a control of like, it's a bit different. So it has kind of quality of like nature-like, creature-like, or tree-like quality, and also like more artifact, like a tile-like, block-like thing. So that's a kind of point of this algorithm. It can go back and forth because of the certain hierarchy in it. So actually, this is all about hierarchy of behavior of agent is the kind of a main point of this algorithm. But anyway, so using that, and the students kind of build or generated those geometric formation using that. And then, so, but anyway, so that's a type of work, actually more research work. Not, I mean, main work is still kind of for me to build facade or designing facade. That's the main part of my practice, but this is my research interest. And then, but anyway, so that's the kind of new thing I'm trying these days. And then that's all of my presentation. Thank you very much.
Thank you so much, Satoru. It's amazing, everything. We're still delighted, not just for the classes, but seeing all this again. I don't know if there's some questions from the students. Or professors.
I'd like to know how do you take on a project? What's the first thing you have to think about, and what are the ideas? How do you concrete these ideas?
In case of like a facade design, I mean, most of the work I actually do is a facade design part, and then, but of course I have to really talk with the architect, like a design intent and promise, and or sometimes comes with a kind of a limitation of like a material, actually not limitation, idea about material or kind of sensibility they want to express. But the first line is the most exciting part, which I have the most freedom. I just most of the time within the constraints, meaning like I have to use like only flat panel, or I have to use only like cast cement geometry or etc. But within that, I just explore as much as possible. However, when we are talking about constructible efficient, actually, if it's competition, it's different. Competition, yeah, I kind of can go kind of crazier, and then just like a double curvature is fine to do that there. But for construction, actually, most of the time I work with construction projects. So in that case, I start to, well, I maintain the certain rational geometry, meaning most of the thing is rational geometry, meaning flat. Well, I mean, right, it doesn't need to be 90 degree, but there need to be certain grid behind that for the support placement later and etc. But still even if you have like orthogonal grid and you have limitation of like flat panels, and but flat panel can be the triangular flat panel or hexagonal flat panel, etc. Definitely infinite options. So I usually generate as much variation as possible. That's fun part. Although the fun part lasts the shortest. That part needs to happen the quickest, like several days, or longest like 1 week. Then I just usually try to generate as many options as possible with the limited time. Then after that, narrowing the option, then thinking more realistically and then more efficient, and then talking to fabricator or thinking of material thickness, joint, weight, etc. So, but the inspiration is like I work or I like way. Not necessarily like design inspiration, but I have certain kind of vocabulary to use for in that initial phase of like a kind of grid based. So grid based, I still use random, but I don't make the grid random. But panel shape could be random. But that is some kind of my vocabulary. But actually, I can tell my vocabulary is really influenced by MC Escher, the not painter, but like a graphic artist. Do you know who MC Escher is? The kind of illusional drawing artist, but that he's not just graphic artist and then painter and then drawing. He also is a science researcher of crystals and the molecule. That he understands how things stuck together efficiently. So that rationality is in his work. So I'm quite influenced or inspired by the work. So yeah, you could see that kind of sensibility. Yeah.
Thank you, Satoru.
Yeah, I would like to ask you. I mean,
it was great to see the work again. Thank you for that.
Carlos. Carlos, there is a problem with your microphone. Again, I think will you need to turn off the camera again or something?
Well, you can type in chat, I guess.
Yeah.
Danny, there's also a question from a student. She put it on the chat.
Okay.
Oh, yeah.
Okay, I see the question on the chat. Okay, so the question is about if I design like manually or use random command. So basically, I generate all of my designs generated from script. I mean text when processing code. But one thing is so it's not. So, but of course, in initial sketch, I kind of sketched out to like, especially like when I think out the panel, like how they touch together and the way the vertices coming and then like it's. But I start with that. But I still then I code. I write code based on my sketch. Then my sketch is usually about the module and then kind of a formula of that. But one thing I can say is that I have certain kind of criteria, like when I not only design facade panel, but there's all other modeling tasks and the problem and the data modeling I need to figure out. I have the criteria to when to start writing code. When I think I need to click more than 1,000 times, I start code. I rather start writing code. If I know I can finish this task by less than 1,000 clicks, I do the manually. That is faster. But one thing usually happens when you are working with like other team or even not. Usually when you start to like I could design whole facade by just clicking in the random manual modeling, but sometimes something changes in the middle. That's so when I start modeling halfway, something changed, I have to redo. Even if I know this can be done with 500 clicks, if I do the 3 times, and then it's faster to do that in scripting. So, well, Grasshopper. I also use Grasshopper, but anyway, so I don't think that's why you're asking, but yeah, I have certain kind of in terms of speed. So most of the time I care speed, and then because I want to generate many iterations as possible. So for me to work fastest, yeah, I use scripting a lot. Then okay, I see another, yeah. I get the question from Carlos, and then difference between compression and construction. Yeah, so the freedom in competition is regarding okay. Wait. How free are you when you take on the competition or schematic design regarding the future unitization rationalization phase? So kind of depends. If we know, you also kind of need to know what kind of competition that is. Meaning, like sometimes like a client expect constructable or like a rational building. I mean, you can kind of sense that before them. But if not, if the competition is really about like idea type competition, and they clearly client not interested in like a cost and the mostly about idea, in that case, yeah, I can have freedom. Like I can create really crazy facade, and then I don't need to think about the grid. I don't need to think about the unit. And in that case, yeah, just become a kind of free sketching. Not if I don't sketch, but I use script to sketch my idea and generate tons of stuff. So in that case, I can use the agent stuff, swarm stuff. But yeah, in the case of like a construction assumed project, in that case, yeah, I don't do that. I set a grid and I use rational geometry. So, but so it depends. And then, but even when I don't really use a rational approach, I kind of, especially so most of the time, competition is not necessarily need to be that rational and cost efficient, but some computation requires those kind of analysis. But most of the time, no. In that case, I can. But most of the computation, of course, assume construction. So you have to make it look like that can be cost efficient later. So in that case, I don't need to have exact grid, but I need to give sense of grid, and I need to give like, okay, so at least like structure-wise, it's working all right, and it can be aligned, and yeah, okay, it's not floating air, and it doesn't collide easily, and that, but still that with that, yeah, I have full freedom, and that rational process is not. You can do that later. There's a something called pre-rationalization, which you have to design with the idea of the rational quality. But there's also post-rationalization. Actually, most of the rationalization, this unitization is kind of post-rationalization. So in that case, yeah, you kind of know you can do that later, and you can make it look like you can do that later. So most of the computation is like that. So I don't strictly unitize them, but I kind of give the sense of rational quality, although they are not strictly rational. Some portion could be curvature, some portion could be not aligned, but look like could be aligned later. So yeah, in that case, I just generate rules. Then, but what I do is that if I don't need to do the strict rationalization, I can code quicker because the precise alignment takes more time. So I skip that part and I just generate. So usually I just generate more options for me and for architects to explore more design options. Then just pick the most favorable. So that's the answer. And then I think I see another one from Carlos, and then also how seamless is the interoperability of a workflow. Yeah, so I use so my own library, although that's open source and then other people can use, but that's processing. But I specifically built file kind of conversion program from my library called IGO. So my processing IGO library can write Rhino file, and then so Rhino file I have control of all the kind of minor information in Rhino as well. So I can control for the layer to color to line weight, etc. So I can coordinate. So basically, my my processing environment can communicate with Rhino very efficiently, and both sides. Also, I'm still using the older version file format, so it's a bit tricky. But so basically, Rhino to processing quite seamless to me. And then, but between the client, I mean my client, meaning the architect, they might use some other software. In that case, I translate Rhino file to other. Or sometimes I develop a new file generator for their platform. Sometimes that happens. So then, being like, for example, Revit. So I don't really talk to Revit from processing. Although there's a possibility, there's a certain kind of access point I could use. So which I haven't done, but if necessary, I could. So, but anyway, so most of the time, in my case, practice, I use Rhino-based practice, and then Rhino processing and the Rhino to other platform. Then necessary, actually this happened once with Katia. I have to work directly with Katia from processing. So I built Katia script generator, meaning I generated Katia script from processing script. So I wrote a script to generate script, and then that script is executed in Katia, and then Katia can generate Katia geometry inside Katia. So that can happen in Revit as well. So, but anyway, so meaning sometimes computational design work is not only about design and the rationalization, it's also about the data management. Sometimes you need to develop this kind of file communicator, or like a software communication software building is also necessary sometimes. So, but anyway, that's yeah, that's yeah, interesting.
Thank you, Satoru.
Thank you.
Satoru,
Right.
we know it's like 12 a.m. in Japan. Thank you really much for taking the time and to share all your amazing work with us. So I think that's it, and maybe we can please. I mean, I know it's late, but if you want to stay to William Virgil tutorial, well, you can also stay. Okay, so
All right, thank you very much.
thank you, Satoru. So now we will finish today with William Virgil. We'll have he will give us a tutorial. So I will give the honor to Professor Alejandro Alcalá to introduce our talented friend, William Virgil.
Yeah, very talented friend. And thanks for accepting the invitation, William. We're very happy to have you here. And I will read you a short bio just to give the students a glimpse and an idea of your work and your practice. So I will start reading this. So William Virgil is an artist, educator, and Army veteran, co-founder of Prash Collective and Design Faculty at SCI-Arc. William holds a Master of Architecture from the Southern California Institute of Architecture, a Master's of Human Resources, and a Bachelor of Architecture from Florida International University. Besides being a design faculty at SCI-Arc, William has acted as a guest critic at RPI, Syracuse, and Kent State Universities. Before he returned to SCI-Arc, he lectured at the Rensselaer Polytechnic Institute, RPI, School of Architecture, and during his time at SCI-Arc, William taught as an assistant to Frank Gehry in a visiting studio that examined creations of the future and collaborated with Gehry partners. Additionally, he taught the studios and seminars in the Design Cities postgraduate program at SCI-Arc. His works have exhibited both domestically and internationally. Exhibitions include, but are not limited to HelloWorld, the A+D Museum, LCI, LA Creates Innovation Campus, SCI-Arc Public Programs, Familiar Primitives Design Team at One Night Stand LA in Los Angeles, California, Kent Armstrong Gallery, and Arsenal Gallery in Białystok, Poland. Williams' research focuses on examining an architect's role as a visual storyteller through media by utilizing film and compositing techniques. His research operates at the intersection of art, architecture, and technology. He's interested in multidisciplinary formal explorations and design between ordinary objects and eccentric modeling techniques. So please welcome William. Welcome, William.
Thank you, Alex. Daniela, Alex, Spanish, English?
Whatever you want, you choose.
Ok. Entonces mejor voy a hablar español porque yo creo que mi gente aquí ya debe de estar un poquito cansada de inglés.
No tanto inglés.
Sí. Bueno, mucho gusto. Mi nombre es William. Yo soy más que todo un diseñador. Me gusta mucho explorar lo que yo llamo la impredecibilidad de la geometría, explorar geometrías que vienen de diferentes tipos de inspiración. Mucho de mi trabajo yo utilizo un software que se llama ZBrush. Es un software que se utiliza más que todo para hacer sculpting y diseñar characters, qué sé yo, para animaciones y cosas así. Entonces yo le voy a enseñar un workflow bien chulo, para mí es chulo porque es algo fácil y tiene que ver con imágenes y quizás es algo que ustedes ya, me imagino que sus profesores le han podido enseñar de otra manera en Rhino. So, hay muchas maneras de hacer las mismas cosas y en este caso yo le voy a enseñar mi manera. So.
Para los estudiantes, a lo mejor no tienen que seguir como que paso a paso del tutorial porque tenemos un corto tiempo, pero sí sería buenísimo que presten muchísima atención y que hagan todas las preguntas que se les ocurran, pero no es que tienen que hacerlo directamente en el software para que puedan ver todo. Igual es va a quedar grabado.
Sí, exactamente. Entonces, para comenzar, generalmente, esta es la interfase de ZBrush. es, a simple vista parece compleja, pero es súper fácil. De la manera que generalmente tú comienzas a trabajar en este workflow es con imágenes. So, por ejemplo, yo busqué una imagen de esta iglesia y esa imagen yo la traigo a Photoshop y la convierto en algo que se llama alfa. Entonces el alfa sería algo así. Alfa no como el cantante, sino así, una imagen blanco y negro. Entonces eso se hace simplemente fácilmente en Photoshop. Puedes venir y darle aquí donde dice Edit, perdón, Imagen, Adjustment, y después puedes darle donde dice Threshold. Entonces cuando le das un Threshold, te convierte la imagen en blanco y negro. Tienes un poquito de noise que te da la imagen cuando la transformas a blanco y negro. Entonces, generalmente, de la manera que arreglas eso es que puedes copiar la imagen. No, me imagino que saben un poquito de Photoshop, por eso, si no, me pueden preguntar. Pero puedes copiar la imagen y la puedes llevar a Illustrator. Y en Illustrator la pegas. Y entonces Illustrator tiene esto que se llama Image Trace. Entonces le das y lo que hace eso es que esas curvas y esa bulla, el noise que tenía la imagen, hace la imagen un poquito más sharp. ¿Ok? Entonces ya después que termina eso, puedes copiar la imagen, traerla de nuevo a Photoshop y después que la traes a Photoshop, tienes dos maneras de proceder. El workflow con el alfa, de la manera que funciona es que lo que sea que es blanco, lo convierte en geometría. Y lo que es negro siempre va a cortar. Entonces, en este caso, yo voy a mantener una imagen así, donde el negro se queda como la imagen es. Y en otro caso la voy a invertir y esta base blanca me parece que la definición de esta orilla me va a dar un borde muy fuerte. Entonces voy a utilizar la definición de esta curva que está aquí para modificar un poquito este lado. Entonces eso simplemente puedo copiar esto. Simplemente le doy layer via copy. Puedo mover más o menos aquí. Simplemente para modificar el borde que me está dando ahí. Entonces simplemente lo voy a hacer rápido. Quiero modificar el borde para que no me dé eso tan raro. Entonces, sigo aquí. Ok. Ya pego estas tres partes. Merge layers. Ok, entonces la imagen tienes que grabarla como una JPG. Entonces simplemente save as y la grabo aquí como una JPG. JPG. Y también voy a grabar esta simplemente para que vean lo que decía del borde. File, save as. Ok, entonces aquí vamos a ZBrush. So, cuando abres el interface, puedes venir aquí donde dice Lightbox y puedes escoger este que dice aquí Polysphere. So, así más o menos es que comienzas el canvas. Aquí donde está esta esfera se llama el canvas, ¿verdad? Para navegar con el clic izquierdo del mouse, puedes hacer orbit. Si presionas Alt y le das clic derecho y sueltas Alt, puedes hacer zoom in and zoom out. ¿Ok? Lo mismo puedes hacer aquí. Aquí tienes aquí para hacer pan, aquí tienes para hacer zoom y aquí tienes para mover. ¿Ok? Si quieres que la imagen se centre en el medio de la pantalla, puedes darle a la F de frame, ¿verdad? Y regresa aquí a la imagen de la pantalla. So, de la manera que ZBrush funciona es que es como si estuvieras pintando, estás esculpiendo, ¿verdad? Entonces puedes hacer diferentes cosas. Esto es un poquito una técnica más complicada, pero, o sea, a mí me gusta enseñarle a mis estudiantes porque me parece un poco divertido, es como si estuvieras pintando. Muchas cosas puedes hacer de esa manera, pero el workflow que yo le voy a enseñar hoy es un poquito más simple. Puedes comenzar con la esfera. Ahora mismo ves como cuando pinto tiene simetría. Entonces, para apagar la simetría, puedes darle a la X y eso apaga la simetría. Ahora solamente lo que sea que haga, la hago de un solo lado. Si la prendo de nuevo, lo que sea que haga, se hace de los dos lados. ¿Ok? Entonces, simplemente para hacer undo, le puedes dar control Z. Con control Z se le hace undo. Y aquí donde dice Subtools, es como, imagínate en Photoshop, aquí es donde tienes tus layers, ¿verdad? Entonces, vamos a empezar con el primer layer, que sería el primer Subtool, y los vamos a transformar en algo que se llama Shadow Box. So, vienes aquí donde dice Geometría. Después, aquí tienes un botón que dice Shadow Box, ¿verdad? Entonces, tienes que prender el Shadow Box. Antes de que lo prendas, tienes que darle más resolución. Aquí, donde dice 128. Lo voy a dejar así simplemente para demostrar la diferencia. Entonces, si lo dejo en 128 y dejo el polish en 10, ves como la esfera, en vez de ser una esfera, se transforma en, no sé, otro tipo de geometría que un poquito esférica, pero al mismo tiempo no. De la manera que el Shadowbox funciona es que imagínate la imagen que yo dibujé en Photoshop. Lo que sea que está pintado negro aquí, en realidad viene siendo blanco. Y lo que está aquí blanco viene siendo negro. Entonces, por eso la esfera, aquí en esta manera, en estas partes, se corta. Porque esto está cortando la geometría que viene aquí. ¿Ok? Entonces, generalmente, antes de comenzar el Shadowbox, yo le subo la resolución para que mi objeto tenga más geometría y le bajo un poquito el polish. So, aquí le puedo poner más o menos 4. ¿Ok? Entonces, ya con el Shadowbox prendido, ¿verdad? Ves que cuando le bajo el polish, aquí me da como un stepping, que está bien. Después se lo puedo quitar haciéndole smoothing, pero me gusta trabajar así. Entonces, bueno, después que ya tengo eso, puedo hacer control y hacer un clic en el background y mover el mouse. Y eso me quita la máscara que dibujé. ¿Ok? El alfa que tenía dibujado el Shadowbox. So, en este caso voy a comenzar por dibujar una máscara. Para dibujar una máscara tienes que presionar control. Vienes aquí donde dice Stroke y ahí puedes seleccionar que dice Drag Rectangle. Aquí donde dice Alpha es donde puedes venir y subir esas imágenes que que enseñé cómo hacer previamente. Entonces aquí puedes hacer import, alfa, y por ejemplo voy a coger esta, fue la primera que hice, ¿verdad? Entonces para dibujar, imagínate que esto es, qué sé yo, como un canvas de Photoshop, puedes hacer control, clic y expander, ¿verdad? Pero si te fijas, el borde está saliendo como un poquito no tan claro. De la manera que puedes arreglar eso es cuando presionas control para la máscara, puedes bajar aquí el focal shift y entonces ahí dibujas, ¿ves? Y ya tus bordes son un poquito más claros. Entonces ya vamos a poner ahí, ¿verdad? Y eso me produce ese tipo de geometría. ¿Ves? Entonces, de esta manera, tú puedes comenzar a dibujar, vamos a poner, lo voy a hacer con algo un poquito más simple. So, si dibujo este círculo aquí y me voy a este lado y dibujo otro círculo aquí, entonces este círculo está cortando este, ¿verdad? Pero entonces puedo dibujar otro círculo aquí y me crece un poquito ahí abajo y puedo dibujar otro aquí y entonces se me corta y así me da ese tipo de geometría. Si quiero que esto crezca, puedo hacer otro allá, otro aquí, ¿verdad? Y así vas más o menos controlando la geometría y dibujando cosas que son un poquito más naturales y no son tan forzadas. Entonces, después que haces eso, ¿verdad? Vamos a suponer, te gusta esa parte, puedes venir aquí y duplicar esto. Entonces ya ese se te queda aquí. So, puedo apagar ese ahí y venir a Shadow Box, apagarlo y ya esto es una geometría. Entonces, de la manera que esto te puede ser útil es que puedes hacer diferentes tipos de geometría y eso puede ayudarte a crear tu proyecto. Y comienzas a crear diferentes como módulos y después utilizas los módulos para generar geometrías un poquito diferentes. So, aquí yo tengo un ejemplo de diferentes alfas, entonces simplemente lo voy a usar para que ustedes vean la posibilidad de cosas que pueden utilizar. So, lo mismo, le hago, quito la máscara, regreso y le doy aquí para importar otro alfa. En este caso voy a coger la mariposa. Tienes que asegurarte que esto sea un JPG. En mi caso dice que es, pero lo voy a volver a grabar porque no se está poniendo. So, ok, voy a utilizar otro. Entonces voy a borrar la máscara y entonces aquí voy a comenzar, tengo que escogerlo. Voy a comenzar a más o menos dibujar. Aquí tengo eso, me da ese pattern. Puedo venir ahora y añadirle, supone añadirle una esfera. Entonces aquí lo miro, me está dando más o menos esto. Entonces, esta esfera, si quieres hacer lo contrario de que quieres borrar la máscara, puedes hacer control y alt al mismo tiempo, lo presionas y dibujas y eso dibuja el inverso. Entonces como que limpia la máscara, ¿verdad? Entonces aquí dibujé eso, vamos a poner eso me gusta, o simplemente aquí le doy duplicate para duplicarlo y dejarlo ahí como geometría. Voy, apago el shadow box, ya se me queda ahí como geometría. Regreso aquí arriba y sigo probando diferentes maneras de dibujar. So, aquí voy a hacer otro círculo. So, eso ya me cambia el contorno de la manera que esto se ve. Voy a dibujar otro de este lado para que me haga un hoyo. Bueno, me lo hace un poquito más pequeño. So, esto también me parece que más o menos puede funcionar. Déjame simplemente, ve cómo me lo cortó aquí. Entonces lo voy a tratar de hacer un poquito más sólido ahí. ¿Ves? Y así pueden ir dibujando. Entonces, eso es lo que me gusta de trabajar de esta manera, de que puedes ir, o sea, si tú te lo imaginas y lo puedes dibujar, puedes simplemente traerlo a ZBrush como una imagen y comenzar a crear. No solamente tienes que puedes utilizar varios alfas a la misma vez. Aquí puedes importar otros, o en este caso voy a importar, a ver, entonces aquí puedo, ok, so ese lo voy a dejar así, solo voy a duplicar, voy a geometría, apago el shadow box para que me quede ese pedazo de geometría, después regreso aquí, quito la máscara, regreso y ahora voy a pintar y sigo escogiendo. Tengo, o sea, para el ejemplo de hoy hice varios, entonces simplemente está a la discreción de ustedes como quieran o lo que quieran utilizar. De esta manera, puedes utilizar diferentes tipos de patterns que te pueden ayudar a conseguir algo bien chévere. So, en este caso, utilicé Mickey. Voy a volver aquí a usar Puedes hacerlo abajo también y eso lo que hace es que va cortando lo que estás haciendo. Todo eso me gusta también, simplemente lo duplico. Voy a geometría, apago el shadow box y puedo regresar y seguir. Entonces, vamos a poner ya después que ya tengo todo este tipo de geometría que me gusta. Entonces, puedes prenderlas todas, ¿verdad? Y puedes comenzar a simplemente a organizarla de manera diferente, de acuerdo a cómo sea tu proyecto, lo que sea que estés haciendo. En este caso, puedo más o menos mover esto aquí. Para traer el combo, simplemente presionas W, o puedes presionar la E o la R, ¿verdad? Entonces, como Rhino, aquí puedes manipularlo, moverlo. Aquí puedes expanderlo o puedes hacerle stretch de esa manera. Nunca lo haría de esa manera, siempre lo haría uniforme en el medio, así. Y aquí puedes rotar, ¿verdad? Entonces, después que generas diferentes tipos de geometría, ya está en ti como diseñador cómo haces para organizarlas en una manera que la geometría pueda trabajar para lo que sea que tu proyecto necesita. So, no sé, si estás tratando de hacer algún tipo de edificación que sea, no sé, ya está en ustedes como decidan usar la geometría que generan, pero conversando con sus profesores, parte de lo que entendí que es lo que ellos están tratando de hacer es cómo enseñarles a ustedes a pensar de una manera donde puedan simplemente divertirse haciendo formas geométricas que son un poquito, no sé, un poco, no sobrenatural, porque tú ves, esto no es, no es nada alien, pero un poquito no tan reconocibles como generalmente uno tiende a hacer cuando uno uno comienza a trabajar. Parte de las cosas más difíciles o de los challenges que yo veo que los estudiantes tienen es, ok, ¿cómo yo comienzo a trabajar con algo que parece un poquito diferente? ¿Cómo puedo hacer algo que sea diferente? Y muchas veces uno ve cosas y piensa, oh, eso es súper complicado, pero son técnicas que uno puede utilizar que hacen que las cosas se puedan hacer fácil y precisa. Simplemente después puedes exportar, vamos a suponer si te gusta esta geometría, puedes exportarla, puedes venir aquí arriba donde dice export y la que tienes seleccionada, das export, la puedes grabar con el nombre que quiera, y le das, la grabas. Y entonces eso puedes llevarlo a Rhino y puedes escalarlo de acuerdo a las dimensiones que tu proyecto necesite. Y sí, eso yo creo que ya concluye mi pequeño tutorial.
Gracias, William. No, súper y súper útil y es como que súper interesante ver cómo se llega como que una forma súper distinta, yo creo que hasta más rápido que hacer una composición de cubos en Rhino o en cualquier otro programa, ¿no?
Sí.
Me imagino que los estudiantes tendrán preguntas, pero no sé si tienes la oportunidad. Nosotros en un curso que hicimos el verano que se llamó Non-Fictional Cities utilizamos 3D Code, que es muy similar, pero sí costó, y lo utilizaron, quedaron cosas muy chéveres, pero sí costó un poquito como que verle a lo mejor como el uso, como adaptar como este tipo de geometrías a algo que pudiese ser como más real, ¿no? Yo no sé si tienes como oportunidad o tendrás a la mano como algunos trabajos de tus estudiantes que me emocionó ver, como creo que lo estás dando en tu GBX en SciArc, ¿no?
Sí.
Que siguen siendo como que súper abstractos, pero es como también, nada, como una manera nueva de modelar nuevas cosas, ¿no?
Sí, sí. Dame un segundo, déjame...
Pero si quieres al final, no sé si los estudiantes tienen algunas
sí.
preguntas.
Sí, si tienen alguna pregunta, por favor. Aprovechen que es en español, no en inglés.
Exacto. Que no les dé pena ya.
Sí, creo que ahora deberían relajarse, ¿no?
Yo tengo una pregunta.
Dímelo.
¿Cuál sería más o menos entonces la diferencia entre este programa y 3D Code? O sea, siento que acá es como más, como que lo puedes controlar más, pero no sé si...
Sí,
no
bueno,
sé.
pues 3D Code, o sea, 3D Code y ZBrush pueden hacer casi las mismas cosas. Para mí en ZBrush tú tienes un poquito más control cuando estás esculpiendo y tienes un poquito más control de hacer operaciones de Boolean que son más fáciles. Esto de generar me parece que cuando estás en 3D Code y estás trayendo los alfas o las imágenes, es un poquito complicado, hay que hacer muchos clics. Aquí, o sea, si te fijas, simplemente presiono control, cambio aquí esto para el brush y aquí simplemente le hago import al alfa. Son procesos similares, pero para mí ZBrush hace el workflow un poquito más rápido y más que de la manera que 3D Code funciona con el sistema de layers, me parece un poquito más complicado que esto aquí con los subtools, porque aquí simplemente es fácil, lo tienes ahí, lo puedes comenzar a editar fácil. Por ejemplo, esto tiene tantas funciones que es tan poquito el tiempo que, por ejemplo, yo puedo simplemente automáticamente hacer operaciones de Boolean sin tener que cortar la geometría. Por ejemplo, lo puedo poner ahí, veis, ya ahí me está cortando la geometría. Y es automáticamente, no es como que tengo que... O sea, por ejemplo, si tú vas a hacer Boolean en Rhino, tienes que hacer la operación y después ves el resultado. Aquí la operación no está hecha y ya yo estoy viendo el resultado, y si no me gusta, puedo, qué sé yo, moverlo aquí arriba. ¿Ves? Es bien interactivo. Me parece que de la manera que o sea, los estudiantes pueden comenzar a utilizar esto, tiene mucho potencial para tú expandir la manera en que tú trabajas con geometrías diferentes.
Ok, gracias.
No, de nada.
Yo tengo otra pregunta.
Sí.
Y es que pues, yo veo que este programa es un poco, pues no sé, puede llegar a niveles de definición pues gigantes. Entonces, pues no sé, me estaba preguntando también que esto, pues si es posible también usarlo como para generar materiales o como para, pues sí, crear materiales para después usarlos dentro de algún otro proyecto o mejor dicho, como hacer como una, pues no solo como una capa de complejidad en material, sino casi que pues comenzar a generar pues, materiales mucho más pues complejos. No sé si, pues mi pregunta es un poco si esto se usa también como en este pues campo de los materiales o solo es, no sé.
Cuando te refieres a materiales, te refieres como a texturas.
Sí, exacto.
Sí. Literalmente este programa, tú puedes crear tus propias texturas. Por ejemplo, si vengo a esta parte, ZBrush, de la manera que ellos empezaron, era así. Ellos comenzaron haciendo texturas. Por ejemplo, por eso tienes como esta paleta de colores, donde puedes venir y por ejemplo, puedo coger esta geometría, decir aquí, Fill Object, poner está ahí, hacer aquí Fill Object. Entonces ya se me pintó verde, ¿verdad? Pero entonces puedo venir a apagar aquí, prender este que se llama aquí mRGB, y entonces ahora puedo coger otros colores, ¿verdad? Y déjame solamente trabajar con este. Y puedo pintar, ¿ves? Estoy pintando mi alfa. Entonces eso ya ahí es simplemente una imagen. No se ve tan sharp porque no tengo mucha geometría, pero si subo el nivel de geometría, ahora lo que sea que pinte, ¿ves? Se pone muy bien bacán. Pero sí, puedes crear tu propia geometría, diferentes, puedes importar texturas que bajes del internet, puedes utilizar cosas como, vamos a poner, aquí tengo esto que es como paja, entonces puedo aquí, ahí, ¿verdad? Entonces ya con esto mismo puedo comenzar vamos a poner, y esto porque tengo este alfa ahí, ¿verdad? Porque puedo cambiarlo a esto, ponerlo un poquito más pequeño y entonces puedo hacer así. Y entonces ya ahí me dibuja la textura. Entonces ya después te lo puedes exportar, puedes hacer render, no sé, Rhino, Maya, lo que sea que estás utilizando.
Y también como que pueden importar geometría que hayan hecho en otro programa, le pueden dar como que un fold también acá, pintarla y luego pasarla al otro programa, ¿no? Eso me ha parecido siempre como un Photoshop tridimensional, una cosa así.
Tridimensional, sí, exactamente, sí. Y definitivamente, o sea, yo les recomendaría que probaran, o sea, utilicen todo lo que sus profesores puedan enseñarle para explorar cosas que son diferentes y una manera, no sé, a mi parecer, bien divertida de approach el diseño, porque más que todo me parece que cuando estamos estudiando tenemos que estar bien abiertos a la posibilidad de lo que el diseño pueda brindar a la profesión.
Vale, gracias. Perfecto.
Entonces,
pronto.
Espérate, entro rapidito al miro de mi clase. Esta es la clase que estoy dando ahora y más o menos aquí puedo enseñarle un poquito el proceso de lo que los estudiantes han estado haciendo este semestre. Estamos diseñando una escuela, pero comenzamos diseñando la geometría, perdón, el furniture de la escuela. Entonces los estudiantes comenzaron diseñando una silla, después una mesa, etcétera, etcétera. Estos son estudiantes que, al igual que ustedes, nunca habían tenido ningún tipo de experiencia con ZBrush. Y generalmente la manera que yo comienzo es dándole un ejercicio de cómo diseñar un cuchillo. Y bueno, ya van a ver, esto dura un poquito para hacer loading. Pero si tienen otra pregunta, por favor. Y Daniela, si me necesita cualquier otro día que lo vuelva a hacer, con más calma, tal vez con, no sé, un grupo más pequeño, funciona un poquito mejor, donde ellos puedan seguir y le enseñamos un par de cositas bien.
Sí, perfecto.
Bueno, no quiere funcionar, ok, ya. Cada estudiante, yo siempre hago el ejercicio con ellos. Esta es mi versión y esta es la versión que cada uno de ellos comenzaron a hacer. Eso es simplemente un tutorial simple que ellos van siguiendo, ¿verdad? Entonces, después que hacen esto, entonces yo le digo, ok, bueno, ahora cada quien tiene que diseñar una silla, ¿verdad? Y entonces yo hice mi ejemplo, este es mi ejemplo. El estudio de la manera que funciona es que estamos estudiando diferentes criaturas, animales, y cómo podemos utilizar los features de esos animales para implementarlo en el furniture, ¿verdad? Entonces, un ejemplo, igual siempre hago un ejemplo, le hago un ejemplo para que ellos vean. Entonces, cada uno de ellos comenzó a hacer su propia versión. Entonces, si te fijas, esto definitivamente estaba horrible, pero después vas a ver lo que ese mismo muchacho comenzó a hacer. Entonces, bueno, ya ahí lo mismo es, muchas cosas muy simples, muchos estudiantes simplemente pensaban que eran cortarle las partes y cambiarle las sillas, cambiarle cambiar las patas, no sé, es un poquito confuso al principio, ¿verdad? Pero ya después, este es el proceso, todo este proceso. Pero te voy a enseñar más o menos las sillas que ellos comenzaron a hacer, que vienen siendo estas. Este fue uno que utilizó un rinoceronte, esta utilizó un dragón, estas fueron la que estaba al lado de mí, que utilizó un león. Este también utilizó un dragón. Este es el del águila, se puso mucho mejor, entendió un poquito más el concepto de trabajar. Este utilizó un león también. Y este utilizó, creo que era un perro, estaba utilizando este para crear eso. Y bueno, esta quedó bien chula también. Entonces, después de ahí, lo que diseñaron una mesa, diseñaron una silla, y lo que diseñaron una silla, diseñaron una mesa, Entonces, déjame solamente te enseño un ejemplo rápido aquí. Aquí está la silla, esta es la mesa y esta estudiante también hizo como una pizarra. Déjame ver, este fue el que hizo la mesa de perro, entonces después vino e hizo esta silla, que me parece que está bien chulo. Okay. Y ya después de ahí tenían que hacer sus aulas, tenían que crear un classroom. Y entonces, estos son todo el proceso que ellos estuvieron haciendo. Y este es el midterm de ellos. So, por ejemplo, este es el del perro. So, la idea es que, no sé si han visto el video de Powers of 10. La idea es que comenzamos viendo el objeto y del objeto vamos saliendo al furnishing un poquito más para arriba. Después el aula en la parte de adentro y después de todo eso es como las diferentes aulas, cómo se van a encontrar las diferentes aulas. Entonces esto fue el midterm, hicieron imágenes, hicieron un video y después comenzamos a trabajar en la escuela, que viene siendo donde estamos ahora, pero este no está actualizado. Okay.
Súper. Igual lo pueden revisar. ¿Cómo es que es el Instagram? ¿Es algo así como 2GAX?
Sí, lo mando en el chat. No me sé bien el nombre. Entonces también hicieron este tipo de videos. Pero yo mando el Instagram en el chat antes de irme para que...
Okay.
Pero si tienen otra pregunta, la respondo antes de irme. Simplemente dejo el video ahí para que puedan ir viendo.
No.
Creo que alguien tenía el micrófono prendido, pero es el video, ¿no?
Sí, es el video.
Sí, el video tiene esos sonidos. Gracias.
Bueno,
buenísimo.
Super, William. Tenemos más tiempo y muchísimas gracias por acompañarnos hoy.
No, gracias a ustedes por la invitación y ya sabes, cuando sea que necesiten me dejan saber.
Perfecto. Bueno, yo creo que con esto terminamos por hoy. Mañana continuamos con una agenda muy similar con Gabriel Esquivel, Casey Rem y Nicolás Turki. Y nada, bueno, gracias a todos, espero que les haya servido. No sé si alguien tiene algún comentario final y si no, bueno, ya terminamos, que sé que tienen otra clase.
Muchas gracias.
Gracias, Daniela.
Gracias.
Sí, muchas gracias por organizar.
Gracias a todos.
Gracias a todos, buenísimo.
Gracias.
Bueno, nos vemos mañana.
Bien.
Bueno, hasta luego.
Mañana.
Adiós.
Chao.